kinematics and momentum, or just momentum for now. So let's just not look that difficult. Okay. Then we've got this. All right. Then question 7 on kinematics again. All right. So you've got 3 more questions to go. Let's look at this one now. Question number 5. It says 3 particles P, Q, and R of masses 0.6 kilograms, 0.4 kilograms, and 0.8 kilograms respectively. They are at rest in a straight line. Okay, so initially all of them are at rest right now. Rest like this. They're on a smooth horizontal plane. The distance from P to Q is 3 meters. Okay, distance from Q to R is also 3 meters. You can see that in the diagram. P is projected directly towards Q with speed 3 meters per second. Okay, so Q is projected towards Q at a speed of 3 meters per second. After P and Q collide, P continues to move in the same direction with speed 1.5 meters per second. So after collision between P and Q, so let's write before here and after here. So before collision, P was moving at 3 meters per second to the right. Q was at rest at 0 meter per second. After collision, P continues to move in the right direction, but at a speed of 2 meters per second. Sorry, 1.5 meters per second. Find the speed of Q after this collision. All you have to do is use conservation of momentum. Momentum before collision equals momentum after collision. Momentum before collision, mass of P, that's 0.6 into velocity of P. We're considering the right side positive. So 0.6 into 3 plus momentum for Q, that's a 0 because it was at rest. That should equal momentum after collision. That's 0.6 into 1.5 plus 0.4 into VQ, and that should give you the value for VQ. You can see what that turns out to be. 3 into 0.6, that's 1.8. 1.8 equals 0.6 into 1.5, that will be 0.9 plus 0.4 VQ. VQ equals 0.9 divided by 0.4, which is 9 over 4, which is 2.25. That's the final result that we get. That's the speed of Q after collision. Okay, 2.25 meters per second. Fairly straightforward. That's all that you have to do here. Let's move on now. This was 5A. What about 5B? It says, in the subsequent collision, between Q and R, these particles coalesce. Find the speed of the combined particle after this collision. Okay, so now what happens is Q and R collide. Now Q was moving to the right at what speed after this first collision? 2.25 meters per second. And in this collision now, the particles coalesce. Okay, so again, momentum before collision should equal momentum after collision. Now we're focusing on the second collision. Now, so just focus on Q and R now. Okay, momentum before collision for Q, it's 2.25 into 0.4, right? It's after the first collision has already occurred. So 0.4 into 2.25. Before the second collision, this is the momentum for Q. 0.4 into 2.25. Momentum for R, that's a 0 because that was not moving, that was at rest. That should equal momentum of the coalesced particle. What's the mass of the coalesced particle? 0.4 plus 0.8, that will be 1.2 into velocity of the combined particle. Let's call that particle C, the combined particle. So VC, what does that turn out to be? 0.4 into 2.25, that's 0.9. 0.9 over 1.2, that will be 0.75. 0.75, that's the velocity or the speed of the combined particle. Okay, that's the second part. Now it says find the time that it takes from when P is initially projected until the instant at which P collides with the combined particle. So now we're looking for the time. Now the surface was smooth. Okay, it's a smooth surface. If it's a smooth surface, that means there's no friction. Okay. If the surface is smooth, there is no friction. There are no horizontal forces acting. That means whatever velocity a particle is moving at, it will keep moving at that velocity. There is no deceleration, there's no acceleration. So you can use the simple speed equals distance over time formulas, time equals distance over speed formulas. They will work here, right? Okay, now how do we use them? Let's understand the situation step by step. We've got three particles. There's particle P, there's particle Q, and there's particle R. Let's talk about the first collision first of all. The distances between these particles initially were how much? 3 meters. Now, initially what happens is, we want to find the total time, right? Initially, P was projected at a speed of 3 meters per second to the right side. How much time does it take to reach the point Q first of all? So that's the time for the first collision. Let's write that down here. Time until first collision. What would that be? Since there's no acceleration, acceleration is 0, we can use the simple speed equals distance over time formulas, or time equals distance over speed. That's what I'm going to use here. Time equals distance over the speed. What does this turn out to be? Distance is 3, speed is 3. That's 1 second. So until the first collision, 1 second passes. All right. Now, what happens after that? Once P has collided with Q, P continues to move towards the right side at 1.5 meters per second. So now what happens is P has reached this point. So I'm going to erase the previous working here. Maybe just keep it like this. This is 3 meters. This was 3 meters. So now the situation is P and Q, they have reached this point. Both of them are at this point. P is also here now. Now P is moving to the right side at 1.5 meters per second. And Q starts moving to the right after this first collision at a speed of 2.25 meters per second. R is at rest there. Okay. How much time does it take for Q to go and collide with R now? Let's find that. That would be time until second collision. Or you can say time between first what's this? 3 over 2.25? 3 over 2.25. What's this value? It's 4 over 3. Okay. All right. So let's just keep it like that. 4 over 3. That's the time between second and first and second collisions. Now the problem is, while Q is moving to the right, how much time passes? 4 over 3 seconds. P would also be traveling to the right side. So at the point of the second collision, Q and R, they are going to be at this position. Let's call this the combined particle now. It's going to be here. P would have also moved some distance to the right in that time. How much distance would it have moved already to the right side? How do you find that? Let's write that down here. Distance traveled by P in this time. 1.5 meters per second, that's the speed, into the time, that's 4 over 3, and that will give you some value. What's this? 4 over 2, that is 2. 2 meters. So P would have reached this point here. Okay. And it is still traveling. It is still traveling at 1.5 meters per second when it reaches this point. And the distance between P and C, therefore, since it has traveled 2 meters, the remaining distance that we've got is 1 meter. All right. And C is now traveling. The combined particle is traveling at 0.75 meters. Combined particle is traveling at 0.75 meters to the right. 0.75 meters per second to the right. When are they going to collide with each other again? Now, think about it. We've done similar questions like this before. Every second, what happens is, every second, in 1 second, let me use a different color for this, because this is the last part of the journey. I represent it in a different color. Okay, so P is now moving at 1.5 meters per second. So every second, what happens is P moves to the right by 1.5 meters. And C moves to the right by 0.75 meters. What happens to the distance between them? P is traveling 1.5 meters, C is traveling at 0.75 meters. The distance between them reduces by the difference between them, 1.5 minus 0.75, and that's 0.75. So every second, what's happening is P and C, they are getting closer. They're getting closer by 0.75 meters. So we can say the net speed, the relative speed for both of them. What would that be? Relative speed for P and C. Relative speed of P with respect to C. P is moving on 1.5 meter to the right. C is only moving 0.75. How much closer do they get to each other? 1.5 minus 0.75. So every second, the distance between them reduces by 0.75 meters per second. So the total distance between them was 1 meter. How much time would it take to cover that 1 meter distance? Time taken between second and third collision now, when P combines with C again, what would be that time taken? The distance, that's 1 meter. The relative speed for both of them, that's 0.75, and that will give you some value as well. 2 over 1.5, and that's 4/3. This is also going to be 4/3. That's the time taken for the last part of the journey as well. What's the total time taken now? The total time taken would be the sum of all those values. 1, 4/3, and this 4/3, and that will give you the result 1 plus 4/3 plus 4/3. That's 11/3. That is your final answer. Or you can say that's 3.66666, 3.67 seconds. That's the time taken. It's very hard to focus on the working because I'm looking at the chat and looking at another screen. So if I try to be very quick, it actually increases the number of careless errors that I'm doing as well. But I'll try my best. Let's see what happens. Okay, so A is projected vertically upwards from this point O. So let's say we've got this point O, and A is projected from this in the upwards direction at a speed of 80 meters per second. There's another point, there's another particle that's projected, that's B, and that's projected at a speed of 100 meters per second. But this was projected 1 second later. B started 1 second later. Okay, keep that in mind. At some point then, they collide with each other. So what's the journey going to look like? B is going to go upwards, and at some point, it's going to start coming downwards, right? And then similarly, A is going upwards. At some point, it's going to start coming downwards as well. At some point, what happens is they're going to collide with each other. They're actually in the same line. I'm representing them separately, just to make sure that you understand what their speeds are. And since they're projected at different times, I want to represent them here on the diagram on the side as well. But they're actually on the same line. That means if their height ends up being the same at some point, let's say they reach this point, they reach the same point at the same time instant. At that point, they're going to collide with each other. Let's call this point X when the collision happens. The information that we have about these two particles is that their initial velocity is 100. That's their initial velocity. We know the acceleration. Since both of them are projected upwards, we can take upwards positive for both of them. We can say the acceleration for B is -10. For acceleration for A is also -10. So we know their initial velocities. We know their accelerations. What about their time? Do we know anything about their times? We know that one was projected 1 second later. B was projected 1 second later. If I were to call time taken for B, if I were to call time taken for B, or let's say time taken for A, if I were to call that T, what would be the time taken for B? The particle that is projected, later, and it reaches the same point at the same time instant, that will take less time. So if time for A is T, the time for B will be T minus 1. So think about it this way. Let's say A was projected at time equals 0. Then B was projected 1 second later. So it was projected at time equals 1 then. If they reach X at the same time instant, that means let's suppose they reach at time equals 10, then how much time does B take? B takes 9 seconds. How much time does A take? It takes 10 seconds. So whatever is the time taken by A, the time taken by B is going to be 1 less than that because it was projected later. Okay? So time for this is T minus 1. What about displacements? At the point when collision happens, they are at the same height. So their displacements are going to be equal. So what we can do now is we can say, let's equate their displacements. S, B, and SA, they should be equal to each other. So we equate both of them. And that's going to give us the value for T, and that's what we are looking for. Initial velocities were given. We found the times. If time for A is T, this is T minus 1. You could also do it the other way around. If you consider the time for B as T, then this time would have been T plus 1. All right. But since they want the time from the start, A was projected first. If we want the value of T directly, we should take the time for A as T, and the time for B would be T minus 1. What about acceleration? Both the particles are projected vertically upwards, right? They're in the air, right? Assuming there's no air resistance. It's free fall. It's motion under gravity. In free fall, acceleration is 10, right? That's a fixed value. We know that. If upwards is positive, gravity acts downwards. So acceleration value is going to be -10 for that reason, because we're taking upwards positive. Okay. So now what we have to do is we just have to equate their displacements. What equation of motion can we use for this? We know that S equals ut plus half at squared. Let's input values in this. For B, we can say it's 100t plus 1/2 into A, which is -10 into t squared. That should equal SA, which is u, which is 80, into t plus 1 over 2 into minus 10. Sorry, for b, the time was t minus 1. I wrote this as t. This was t minus 1. And here as well, it's supposed to be t minus 1. The time for b was t minus 1. So for a, it's half into minus 10 into t squared. This is what we get. Now we simplify this and find the value of t from this. What do we get? We have 100 t minus 100. From this, we get minus 5 into t minus 1 whole squared. What does that simplify to? T squared minus 2t plus 1. On the other side, we have 80t minus 5t squared. Let's simplify this. 100t minus 100 minus 5t squared plus, no, minus 1 is plus, that's 10t minus 5, that equals 80t minus 5t squared. Take all terms to one side. We've got 100t, 10t minus 80t, that will be 30t. Minus 5t squared and minus 5t squared, they're going to get cancelled. Minus 105, that equals 0. T equals 105 over 30, that will turn out to be 3.5. So the value of t that we were looking, that is 3.5. That's our final answer. Is that okay? Any problems with this? So it was free fall. We just wrote down their values. We equated their displacements. If time for A was t, this is important. Time for B will be t minus 1, the particle that's projected late. All right. Okay, so that's part A. Part B says, find the height above O at which the particles collide. Height above O at which the particles collide. So we just have to find the displacement value, right? You can either use this equation or this equation, any of them. That should give you the result. Let's use SA. That was 80 times T, 80 times 3.5 plus 1 over 2 into minus 10 into 3.5 squared. And that will give us the height that we need, because the displacement for A until that point and the displacement for B until that point, they're both the same. You can use any of these two equations and that will give you that height. What do we get? What's this value? 218.75. Thank you. 218.75. That's the result that we're getting from this. Okay, so that was part B. Let's move on. These first two parts were fairly straightforward. Now it says find the time from A being projected until C returns to O. So now we've got momentum, kinematics. It's that part. I would recommend leave it for the end generally. But let's do it now. Okay, so they coalesced to form particle C. Now we've done some calculation already. So the situation is like this. O is here. Particles A and B, they have collided at this point. Let's say which one had greater speed. A was projected earlier. So A would be up here. B would be here at the time they collided. At what height were they at this point? We found that in the first part, this height was 218.75. Now, when they collide with each other, they coalesce and become one single particle. And then that one single particle has to return to the point O again. So first of all, we have to use momentum to figure out the speed of that coalesced particle after collision. Okay. How do we determine that? Do we know the final speeds for A and B? We don't know that. At the point when they collided, we don't know what the speed of A was. We don't know what the speed of B was. So first of all, we have to find those speeds. Okay. So first of all, let's find the speeds before collision. Let me mark these points. Let's say this point is O. At the point of collision, let's call this point X. So from O to X, let's find the final speed for both of them. We're considering upwards positive for both, right? What's the velocity for A, final velocity for A, and what's the final velocity for B? We've done the we know all the other information from the first part. Initial velocity for A was 80. Let me write that down here. So I'm using V equals U plus 80. V equals U plus 80. 80 plus A was minus 10, times T, which was 3.5. And that will give us the final velocity of A and B, their velocities just before collision. Let's say what they turn out to be. For B, it was 100 plus minus 10 into 3.5. From the first one, we get 45 meters per second, right? And from the second one, we get 65 meters per second. So we know that before collision, A is moving upwards. A is moving upwards at 45 meters per second, and B is moving upwards at 65 meters per second. It's 75? Oh, okay, 75. I'm sorry about that. So one was T, the other was T minus 1. Sorry, I missed that. This was time for A was 3.5, right? But B was projected later. It was T minus 1. We used just 3.5 there. It should have been 3.5 minus 1. That's 75 actually. This is 75. Okay, this is 75. Now what we know is that A is moving up at 45 meters per second. This is before collision. And B is moving up at 75 meters per second. How do I represent them? Let's write them like this. So this is A, and this is B. This is moving up at 75 meters per second. This is before collision. This is before collision. Both of them are moving up. I can take upwards positive. Okay. What happens after collision? After collision, they coalesce and become one single object. And that's one single object is C. And we don't know what the velocity for C is. Let's call that VC. Now, do we have their masses? Do we have their masses? Okay, so they have the same mass. That's all that they're telling us. They have the same mass. Okay. So if they have the same mass, then we can say if this is m kilograms, this is also m kilograms. And C would then be m plus m. That's 2m kilograms. Okay. That's 2m kilograms. Now let's apply conservation of momentum. Momentum before collision, that equals momentum after collision. What do we get for this? Momentum before collision, we're considering upwards positive. Mass of A, that is m, into velocity of A, that's 45, plus mass of B, which is m, into velocity of B, that's 75, that equals mass of C, which is 2m times velocity of C. Now m is going to get cancelled for all of them, and we get the velocity for C. What does that turn out to be? 60, right? Yeah, 60 meters per second. That's the velocity of C that we get for this. All right, because m is going to get cancelled. We can take that common, divide by that. That gets eliminated. We get 60 meters per second. So now we know that coalesced particle, let's represent that on the side now. It is now moving at 60 meters per second. And it's moving in the upwards direction. How do we know that? Value here, that means it's moving upwards at 60 meters per second. All right. Now, what do we know about this particle? We know initial velocity. So now we use kinematics. So for C now, it's projected upwards initially. We can take upwards positive for this. Initial velocity is 60. Gravity acts downwards. So acceleration would be negative 10. What else do we know? We know the displacement. We want the time until C returns to O, right? What's the displacement going to be? It comes from this point to the point O. It has to go down, right? What's the displacement going to be? We know the height of that point is 218.75. We don't need that. Okay, so we don't need to find the time until it changes direction. We can do it directly. We don't need to break it down. We don't need to break it in two parts like this, that we find the time until it goes to the maximum point, and then from the maximum point to the ground. We can do it directly. Direction would matter. So let's understand this. Initial velocity was 60, right? We are saying upwards is positive. Acceleration is -10. What about displacement? It goes from C to this point O. It goes from that point X to the point O. It's going down. We are considering upwards positive. So what is displacement going to be? We say displacement is going to be -218.75. So displacement sign will be negative here. It doesn't matter what the particle is doing in between. It can go up, it can go down. Eventually, all that matters is what's the displacement. And in displacement, only the starting point and the end point matters. Okay, only the starting point and the end point matters. It's going down, so displacement is negative. That's it. It can do anything between motion, in between those 2 points, and that would not matter. So we know that initial velocity is 60, acceleration is -10, displacement is -218.75, and we need to find the time taken for this journey. Let's see what that turned out to be. S equals ut plus half at². What does this turn out to be? -218.75 equals 60 into t plus 1/2 into -10 into t². And you can find the value of t from this. A changes sign in between. A does not change sign in between. Acceleration only depends. Okay. Acceleration sign only depends on the positive direction that you've taken. It doesn't matter if the particle is going up or down. It does not depend on that. You are considering upwards positive throughout the journey. Throughout the journey, we're considering upwards positive. Okay. Gravity is acting downwards throughout. That's the only thing on which the acceleration's sign depends. The particle can go up, down, that's irrelevant. What matters is your positive direction. We are taking upwards positive throughout the journey. Gravity acts downwards, so acceleration is negative. Okay? Acceleration is negative throughout. You can think of it like this as well. It started from 60 meters per second. When it's going up, its velocity will be decreasing. It will become 50, 40, 30. So it will reduce to 0 meters per second at some point. So it's going from 60 to 0. It's negative acceleration. When it goes down, its velocity becomes negative now. Its velocity becomes -60 meters per second here. At this point, when it hits the ground, again, it's going to be some negative value. So maybe 100 meters per second at some point. Throughout, the velocity is decreasing. It's going from 60 to 0, and then from 0 to a negative value. It's decreasing throughout. Velocity is a vector quantity. It's decreasing throughout the journey. So acceleration remains negative throughout the journey if you're taking upwards positive. Okay, so throughout the journey, A is -10. All right, so now we can just find the value of t from this and see what that turns out to be. -218.75. Okay, let's just quickly solve this. I'll answer a question. -218.75 equals 60t minus 5t². Let's take everything to one side. 5t² minus 60t -218.75 equals 0. All we have to do is input values in the quadratic formula. T equals minus into -60 plus minus square root of -60 whole squared minus 4 into 5 into 218.75. Negative 218.75 divided by 2 times 5. What are the values of t that we get from this? 14.93 and minus 2.93. Thank you. Time cannot be negative. So this is not possible. This is the only value of time that we're getting. However, in the question they said, find the time taken from A being projected up until C returns to O. So this is the time taken after collision. Before collision, 3.5 seconds had already passed. So we add 3.5 to this, and that will give us the total time taken. The total time turns out to be 3.5 plus 14.93. Write it clearly, 14.93. And that gives us 18.2, 18.3, 18.4. 18.4, right? Yeah, 18.4 seconds. That's the final result that we get. Let's look at this now. Question number 7. Two particles A and B of masses 3 kilograms and 5 kilograms respectively. They are connected by light extensible string that passes the particles are held with the string dart. Okay. The plane released from rest in the subsequent motion A does not reach the pulley, and after B reaches the plane, it remains in contact with the plane. Find the tension in the string and the time taken for B to reach the plane. Okay. You've got the masses of A and B. That's good to know. That's what actually keeps me motivated, those comments from all the students, both in the classes and on YouTube. I hope something good comes out of these sessions, that you do go and do bigger things in life, inshallah. Take us out of the situation. This is one factor. Of course, there are many other factors, our ethical situation, our moral situation. The way are on the wrong side of history every time. And even in our daily situation, there used to be a time when people used to think that, okay, if this person is a Muslim, if he's saying something, we have to trust that it's definitely going to be true. There's no way this person can lie. There's no way this person can deceive someone. And now it's the opposite. Kuch bhi hota hai, to it has to be a Muslim, because we have left all our morals, all our ethics. I teach admaths. I don't have group classes for that right now. I might have that. I have some next year, inshallah, because I'll be reducing some of my school workload, hopefully, if they let me go. If they let me have some free time, I might have 3 days free in a week that I might spend more time on teaching online. Let's see. I do have that in my head right now, that I want to teach more online. And advanced might next year. Try to get back to this question again. Okay, so we've got the mass of A, that's 3 kilograms. So the weight is 30 Newton. That's one thing that we know. For B, we know that the weight is 50 Newton. String is taut. A is 1 meter above the horizontal plane. B is 2 meters above the plane as well. You can see it on the diagram. The particles are released from rest. Okay, so they start from rest. In the subsequent motion, A does not reach the pulley, so A is going up. Mention the string of the time taken for B to reach the plane. Okay, all right. So that's not as difficult as it looks like. So first of all, we've got you've got two objects. You've got two objects that are connected to each other. You've got particle A and you've got particle B. A is moving up in the upwards direction, and B is moving in the downward direction. What are the forces acting on A? There's tension acting upwards. There is weight acting downwards. For B, there's tension acting upwards. There's weight acting downwards. A is moving upwards, so the forward force for A is T. The backward force for A is 30. That equals mass of A, which is 3, into acceleration. That's one equation that we have. For B, the forward force is 50, the backward force is T. That equals mass of B, which is 5 times acceleration. We can find the tension now and the acceleration as well, because we will need that to find the value for T here. Let's find both of those values. We can make T the subject. T equals 30 plus 3 times A, and from this, T equals 50 minus 5 times A. Let's equate both of them. 30 plus 3A, that equals 50 minus 5A. 8A equals 20, and then A equals 2.5. All right. Okay, so then you can find the value of tension. Tension equals 30 plus 3 into 2.5, and that gives us 37.5, right? 37.5 Newton. So we've got the acceleration, we've got the tension. Tension was what they were asking for. That was one thing that they were asking for. What about acceleration now? Acceleration is in fact 2.5. What about the time taken? B is moving downwards. We know the initial velocity. It started from rest. We know the displacement, that is 2. We know the acceleration. We can the downward direction positive for B. So what do we know about B? We know the initial velocity, that is 0. We know the acceleration, that is 2.5. We know the displacement, that is 2. And we have to find the time taken. Which equation do we use for this? S equals ut plus half ut squared. S equals ut plus 1 over 2 into at squared. That's 2 equals 0 into t plus 1 over 2 into 2.5 into t squared. And that gives us 4 over 2.5. And then you take square root of that. What's the time taken? 1.26 to 3 significant figures. That's the second thing that we were looking for. A very easy question at the end of this paper. Part A at least, right? But a lot of you have asked about it. So maybe the second part has something. That was the first part of Let's look at the next, not that complicated. All right, now how do we think about this? You see B is moving downwards. By meters. What about A? A would also move up by 2 meters. So let's say A comes at this point here in that time. Okay, so A reaches this point. It travels another 2 meters in that time. It was already 1 meter above the ground. Okay. That is when B hits the surface. That's when B hits the surface. It hits the surface. So A at this point is at a height of 3 meters. Now at this point, the string will become slack because B has hit the ground. The string will no longer be taut. The string will become slack at this point. So now we can consider this situation. We can say you have this point, you have this particle A. It's here in this position. Such that its height from the ground is how much point, its height from the plane, it has to be 3.25. It becomes equal to 3.25. From the starting point, how much more does it have to travel in the upwards direction? 0.25 meters. 3 meters is already this. It has to go 0.25 meters more. Now, what do we know about this journey for A after that? The string is slack. After B hits the plane. What do we know about A? We know acceleration. What's that going to be? There's no tension, yes, because it's the string is slack now. There's no tension. And it's free fall now, right? Since there's no tension, the particle is moving under gravity. The value for acceleration, if you're considering upwards positive, that's just going to be -10. Okay, it's free fall, yes. Now, from its starting point, what displacement are we talking about? 0.35 meters. What we can do is we can put the value for displacement equal to 0.25 for now. Let's find the time instant when the displacement is equal to 0.25. Okay. Let's find the time for the instant when the displacement is equal to 0.25 from the starting point. Now, can we find that? We need one more piece of information. We do not have initial velocity. We do not have. What we can do is we can consider. Okay, just give me a second. Okay, I'll let you know. Just give me a second. I'll be back. Okay, so we're getting late now. I'm getting called by people at home. Okay, so yeah, we are considering this part of the journey. After the string is slack, right? After the string becomes slack, at that point, A is already at a height of 3 meters. We are only starting. This part of the journey is only starting after this point, when A is already at a height of 3 meters. The total height above the plane has to be 0.25 meters, 3.25 meters, sorry. So we only have 0.25 meters left, right? So we're only considering that part of the journey now, 0.25 meters above that initial point. Now we need one more piece of information. Where do we get that from? Before the string becomes slack, we can find the final velocity of this particle A. How can we do that? While the string was taut, we knew that it started from rest. It traveled a distance of 2 meters. We know the acceleration as well. And we also know the time taken for that part of the journey. That was 1.26. We can use all of that. To find the final velocity while the string was taut. Okay, let's find that. So this is for the second part. When the string was taut, what do we know about A? Initial velocity was 0. Displacement was 2. And acceleration we found to be 2.5. Can we find the final velocity from that? we can use b squared equals u squared plus 2as. What does that give us? V squared equals 0 squared plus 2 into 2.5 times 2. And that will give you the value for V, which turns out to be square root of 10, right? This is the velocity at this point. Square root of 10 meters per second. At this point, the velocity is square root of 10 meters per second. That is now the initial velocity for the part when the string is slack. This would be u equals square root of 10. How do you find the value for t now? Let's see what that turns out to be. Which equation do we use? We can use s equals ut plus half at square. S is 0.25. U is square root of 10 into t plus 1 over 2 into minus 10 into t squared. That's an equation that we get. 0.25 equals square root of 10 times t minus 5t squared. 5t squared minus square root of 10t plus 0.25 equals 0. Input values in the quadratic formula. Minus into minus square root of 10 plus minus square root of 10 whole squared minus 4 into 5 into 0.25 whole divided by 2 times 5. And that will give us the result. What's the value of t that we're getting? 0.0926 and 0.53978. 0.53978. Now we're getting two values of t. What does that mean? Two values of t. Now see, the journey of this particle is going to look like this. It goes up. It's going to reach a maximum point. Its displacement from its starting point is equal to 0.25 at 2 points, at 2 time instances. One time instant is when t is equal to 0.0926. That's one time instant. Okay. And the other is on its way back, when its height again becomes this, and that is 0.53978. We wanted to find the time for which A is at least 3.25 meters above the plane. That means we want the time taken for this part of the journey, this yellow part, is greater than that point. So what's the time duration for that part? We find the difference of these two values. The height first became equal to 3.25 at this time, and then it became again the same height at time equals 0.53978. If you find their difference, that will give us the time duration for which the height was above this point. So we say 0.53978 minus 0.926, and that's going to give the result. You can see what that is. 0.447, and that's our final answer. This is the time for which the height is greater than 3.25 meters. That's what we were looking for. Does that make sense? So again, it's that same idea. You have a string that becomes slack at some point. You find the final velocity from the part where the string will start. That becomes the initial velocity for the second part of the journey. So that's what we did. First of all, we found the final velocity while the string was start. That turned out to be this. That became the initial velocity for this part of the journey when the string was slack. We used that to find the time taken until the height becomes equal to 0.25. We got two values from that. One was when the particle was going upwards, the other when it was going downwards. So the time duration comes from their difference. Least or greatest value of a force in context of a question where you have friction involved, what you do is you consider limiting equilibrium, right? In this case, you had to find maximum and minimum, so you could do it like this. Okay, yes, we will complete this, inshallah. Okay, let's move on. Question number 6. Let's have a look at this now. 3 particles A, B, and C of masses 5 kilograms, 1 kilogram, and 2 kilograms respectively. They lie at rest in that order on a straight, smooth, horizontal track X, Y, Z. Initially, A is at X, B is at Y, and C is at Z. Particle A is projected towards B with a speed of 6 meters per second. At the same instant, C is projected towards B with a speed of V meters per second. That's a lot happening. Okay, so we have a horizontal track. Let's represent it in the form of a diagram that will make it easier to understand. So we have this horizontal track like this, okay? And on this track, we have 3 points. One is X, another is Y, and then there's another Z. Let's mark these points like this, X, Y, and Z. And what's happening is A is at X initially, B is at Y, and C is at Z. So X, Y, and Z are points. A, B, and C are particles. So A is a particle, B is a particle, and C is a particle. A is projected towards B initially. So A is going towards the right side. This is the initial state. A moves to the right at a speed of 6 meters per second. That's the initial thing that happens. At the same instant, C is projected towards B. So C projected towards B with a speed of V meters per second. In the subsequent motion, A collides and coalesces with B. So first of all, there's a collision between A and B. Okay, there's a collision between A and B first of all. Now let's talk about this first collision first of all. Particle D then collides with C to form E, and E moves towards C. Okay. So first of all, we have a collision between A and B. Let's just focus on A and B particles. Initially, all the particles were at rest, right? So A is projected towards right, B is still at rest. So let's say this is 0 meters per second. Okay. Now, this is the situation before the first collision. What happens after the first collision? So this is for first collision. What happens afterwards? A and B coalesce and they become a single object. So earlier they were A and B. So afterwards, what happens is they become a single object, and we don't know what the speed of that single object is. Let's say this speed is VAB. Can we find that? Let's try to find that first. VAB. Apply conservation of momentum on this first collision and see what that gives us. Their masses are 5 kilograms, 1 kilogram, and 2 kilogram respectively. So AB particle, that would be 6 kilograms, right? Because mass of A is 5 and mass of B is 1. Let's apply conservation of momentum on this first collision, first of all. Momentum before collision should equal to momentum after collision. What's the momentum before collision? Mass into velocity, right? Mass of A into velocity of A. Considering the right side positive, we can say 5 times 6 plus the momentum of B, that's a 0, because that was at rest, that equals momentum after. Mass of AB, that is 6 into velocity of AB. That's the coalesced particle. In fact, they named it something. They named it D. Let's actually call this D instead of AB. So this becomes a particle D now. So its speed can be represented as VD. Can we find VD from this? 30 over 6, that's 5. So velocity of D after this collision is 5 meters per second. Make sense? D moves at 5 meters per second to the right side. What happens after this is that D is moving towards right, V is moving towards left. And now D and C collide to form E. So now we're talking about second collision. So now we know that there's a second collision that's happening. The before situation is that there is particle D that's moving to the right at a speed of 5 meters per second. And there's a particle C that is moving to the left at a speed of V meters per second. And then they collide after the second they coalesce after the second collision, become a single object E. And the mass of E would then be the total mass, which is 8 kilograms. This would be 8 kilograms. D was 6 kilograms and C was 2 kilograms. Again, momentum before collision equals momentum after collision. Right? Momentum before collision. Before collision, we've got just particle D. Okay. What's the mass of particle D? That is 6 kilograms. 6 into 5 into momentum of particle C that's moving in the opposite direction. Its velocity is going to be negative. So 2 into minus V, right? This velocity would be considered negative if you're considering the right side positive. That should equal 8 into velocity of E. We have to find the velocity of E, right? Let's make E the subject. That's 30 minus 2V over 8. And that simplifies to 15 minus V over 4. That's what we wanted to show there. That's a lot of work for 3 marks. But as I said earlier, that's what happens in the last couple of questions in mechanics paper generally. That's what you would do. Does this make sense to everyone? Any problems? Okay. All right, let's look at the next part now. Part B says, the total loss of kinetic energy of the system due to the two collisions is 63 joules. Use the result from A to show that V is equal to 3. Total loss in kinetic energy is given. Can we find the initial kinetic energy? Initial kinetic energy. What was the initial kinetic energy? We had this moving at 6 in kinetic energy for A. We've got that. For A, it would be 1 over 2 into m, which is 5 into 6 squared, plus kinetic energy of B, that was just 0 because that was at rest, plus kinetic energy of C, half mv squared, that's half into 2 into v squared. That's the initial kinetic energy. What does this simplify to? 36 over 2, that's 18. 18 times 5 is 90. 90 plus v squared. 90 plus v squared, that's the initial kinetic energy. Right? In the very beginning, this is the kinetic energy. Right? When they're moving at these speeds. What happens at the end? At the end, we just have one particle, that is E. So final kinetic energy for that one particle, 1 over 2 into mass of that particle. What's that? That's 8. Mass of E was 8 kilograms, right? That's the sum of all the masses, 5, 1, and 2. That's 8 kilograms in total. Into V squared. Into velocity of that. What's the velocity of this particle? That's 15 minus V over 4 whole squared. That's the velocity of particle E that we have shown in the previous part. 15 minus V over 4 whole squared. That's the final kinetic energy. And that simplifies to, we have 4 outside and then 1 power of that gets cancelled. And that's going to be 15 minus V whole squared over 4, right? We have 16 here and 4 here. We would end up with this. That's the final kinetic energy. Now they are telling us that the total loss of kinetic energy is supposed to be 63 joules. That means the difference between these kinetic energies, that's supposed to be 63. Loss means the initial kinetic energy has to be bigger and the final has to be smaller. If we do final minus initial, let's actually do it that way. Final minus initial, that's how we find the change, right? Change of kinetic energy is going to be final minus initial, 15 over minus v whole squared divided by 4 minus 90 plus v squared. This is going to be equal to what? There's the loss in kinetic energy. That's 63. That means it's equal to minus 63. Or you could also do 90 plus v squared minus this equal to plus 63. You could do it either way. If we do final minus initial, then we're talking about change. Since there's a loss, that change has to be negative. So that's why I put negative there. Now you can solve this equation and see what that gives you. On the left side, 15 minus v squared. Why is it so lengthy? 15 minus v whole squared, that is 225 minus 2 into this, that's 30v plus v squared minus, so I'm multiplying 4 with the equation. That will give me minus 360 minus 4v squared. 4 gets multiplied on the other side as well, and that gives us minus 252. Okay, now this gives us minus 3v squared minus 30v and what's this? 252 minus 360 plus 225, that will be 117. We can divide the whole equation by minus 3 to simplify this. It will become v squared plus 10v plus this over 3. 120 over 3 is 40, so that will be 39. Okay. Can we factorize this? Can we factorize this? We have to show that b is equal to 3. This has to be some problem somewhere. This is minus 117, okay, this was positive, sorry, because that's not factorizing. This is negative then. And that should actually, yes, I'm sorry, this was supposed to be plus here, and it got to the left side. And now it should be, it can be factorized. Yeah, so now this becomes v squared plus 13v minus 3v minus 39 equal to 0. We get two factors from this, v plus 13 and v minus 3. V is equal to minus 13, v is equal to 3, and that is what we were looking for, the value of v turns out to be 3. Okay? Does this make sense? We found the kinetic energies in the beginning, and at the end we found their difference, and we equated that to the difference that they gave us. Okay? And that gave us v equal to 3. Now it cannot be negative because that will mean that it's actually moving in the opposite direction. And so that would mean that C is actually moving towards right. That would not make sense. That's not what the question said. C is actually supposed to move towards the left. That's why we ignore the negative value. Okay, so V is equal to 3. That's the result that we get. Yeah, that's too much work for 3 marks. Sometimes I think that it's probably after they have already given the paper and when they start making the marking schemes, they realize how much work it is for a few marks. Because some papers, this is still kind of, yes, it is also lengthy, but you'll find some papers, they're like impossible to complete in time. It's not possible anyone would be able to complete them in time. But although that's not possible to complete in time, you can still get a good grade in that because that will be difficult for everyone, right? So threshold will take care of that. So there's one particular paper that I remember, I think November 21, some variant of that. It's so long that I think nobody would have done that in time, and threshold for an A in that paper was 28. 28 out of 50. So sometimes that can happen as well, but threshold takes care of that, okay? all you have to do is just make sure you don't get stuck in the middle of the paper, because that is what can do in your grade. Make sure that all the questions that you do know how to do, you complete them first and then leave the more difficult ones for the end. And hopefully you have enough time at the end to be able to complete them. Okay, we have still 2 more parts to go for this particular question. It's given that the distance xy is 36 meters and yz is 98 meters. Find the time between the 2 collisions. Okay. Now it's a smooth horizontal track. It's a smooth track, that means there's no friction. If there's no friction and it's a smooth track, that means the particles are moving at constant velocities. Their velocities are not changing. Okay, they're moving at constant velocity. Okay, now what does that mean for us? This is the horizontal track. What they're telling us is the point X and Y, their distance is 36 meters. And Y and Z, their distance is 98 meters, right? These are the distances between these 2 points. Find the time between the 2 collisions. Time between the 2 collisions. How do you find this? How much time does it take for the first collision? First of all, A started its journey from this point. This was X, this was Y, and this was Z. Now, first of all, A started from here and it went towards B. At what speed was it moving? At 6 meters per second. How much time did it take to reach the point B, first of all? Remember, these are constant velocities. So you can use distance equals speed into time, speed equals distance over time equals distance over speed. Those formulas work here. Why? Because these are constant velocities, okay? So we can use that simple formula. So what's the time for the first collision? Distance is 36 divided by the speed, that was 6 meters per second. Was it 6? Yeah. That is 6 seconds. This is the time until first collision. This is time until first collision. From the start to the first collision, this is the time taken. Now, remember when this happens, when these 6 seconds pass, C had already started its journey as well. At the same instant, C was projected towards B. So C is also moving towards B at the same instant. So C would have already moved some distance to the left side. How much would it have moved? It was moving at V meters per second. What was the value for V? We found that V to be 3 meters per second, right? So C's speed was to the left side, 3 meters per second. Until the first collision, 6 seconds have passed. Until the first collision, 6 seconds have passed. Okay? That means in those 6 seconds, how much would have C traveled to the left side? How much would have C traveled to the left side? 3 speed into time, that is 18. So C would be somewhere here. Let me represent it with a different color. After the first collision, C is here, such that it is a distance of 18 meters from its starting point. Okay. And this is at the point of first collision, right? C is here. And the particle D, that is here, because the collision happened at the point Y. So let me actually represent it here. This is particle D, and the particle C is here at the time of the first collision. Does that make sense? Okay, so what's the distance between these 2 points now? This was 98, this was 18. So the distance that's left is 80 meters. Does this make sense to everyone until this point? This is at the point of the first collision. Okay, at the point of the first collision. This is the position of D and this is the position of C. Now, for the second collision, how much distance do they have to travel? 80 meters combined, right? D has to travel to the right, C has to travel to the left. The total distance traveled has to be 80 meters. Now, what's the speed of D? D is moving at what speed? Speed of D, 5 meters per second. D is moving at 5 meters per second to the right side after this point. And what about C? C is still moving at 3 meters per second. Every second, you see what's happening? In every single second, D moves 5 meters to the right, C moves 3 meters to the right. How much closer do they get to each other every second? 8 meters, right? One is traveling 5 meters and the other is traveling 3 meters in every second. So their relative speed is 8 meters per second, right? So every second, they're coming closer by 8 meters. So you can say their overall speed, or it's actually called relative speed, but that's terminology is not important for you. The overall speed, because this is 5, this is 3, they're getting closer to each other at a speed of 8 meters per second. What's the distance that has to be covered? 80 meters. What's the time taken then? Time taken would be 80 over 8, and that is 10 seconds. That's the time taken from the first collision to the second collision. That's what you get. Does this make sense? Okay. All right. That was part 1. Now let's look at part 2. It says, find the time taken between the instant A is projected from X and the instant that E reaches Z. Yes, this is actually one of the more difficult questions. That's correct. Overall speed nahi samajh aayi. It's actually the relative speed, basically. Now think about this. Let's say you're standing here and another person is standing here. The distance between you two is 10 meters. Okay. The first person moves at 2 meters per second. The second person moves at 3 meters per second. How much time would it take for them to meet each other? Every second. So what happens in the first second? In the first second, this person A moves 2 meters to the right, and the second person moves 3 meters to the left. In the second, this person moves 2 meters more, and this person moves 3 meters more, and they meet each other when time is equal to 2. So you see, every second, what's the distance that they're getting closer to each other? In 1 second, the first person is moving 2 units right, and the second is moving 3 units left. So overall, they're getting closer by 2 plus 3. That's 5. Right? So that's the overall speed or the relative speed, right? Yeah, okay, that's good. So that's what we're doing here. That's the relative speed of both the particles. Now it says find the time taken between the instant that A is projected from X and the instant that E reaches Z. Okay, that A is projected from X, that's the starting point, and the instant that E, that's the final particle, reaches Z. Okay, so now you see what's happening. 6 seconds already passed in the beginning, before the first collision. Then it took 10 more seconds until the first collision. So we have 16 seconds already passed since the beginning. Now we have that particle E. I think examiner was in a bad mood while making this paper. How is that 1 mark? Okay, so now we've got particle E here. At what point that collision happens now? This is Z, and there is particle E here. Now we've got to find the time that it takes E to reach Z. Okay, the time that it takes E to reach the point Z. Now for that, we first need to find at what point the second collision happens. At what point the second collision happens? How do you find that point? That's the question now. Okay, so we knew that this was 18 meters, and we also knew that further it was 80 meters. This was point D earlier, and this was point C. C was moving to the left, D was moving to the right. At what point does collision happen? Collision happens after 10 seconds. The second collision happens after 10 seconds. Right? Collision happens after 10 seconds. In 10 seconds, where would C be? C would have traveled 30 meters, and D would have traveled 50 meters in those 10 seconds. This would be the point where they collide. This is where E would be. So how much distance does E have to cover now? 30 plus 18 to the right side. Okay, E has to cover 48 meters now to the right side. Now, what's the speed of E? At what speed does it cover that distance? What's the speed of E? Do we know that? This was the speed of E, right? 15 minus V over 4. You know the value for V? So you can find the speed of E. That's 15 minus 3 over 4. That also turns out to be 3. So the speed at which E is moving is 3 meters per second. 48 meters in at a speed of 3 meters per second. How much time does it take? 48 over 3, that would be 16 seconds. You would add this number to the previous two values, give you the result. You can see what that turns out to be. That's 6 plus 10 plus 16, which is 32 seconds. And that's your final answer. Okay, I'm sorry on behalf of the examiner. This is let's have a look at the next one. Question number 7, the last question that we have. We'll try to be a bit quick. Hopefully, I said that the last one as well, but we could not be. Let's try this one now. This is the last one. Two particles, P and Q of masses 2.5 kilograms and 0.5 kilograms respectively. They are connected by a light and extensible string that passes over a small, smooth pulley fixed at the top of a plane inclined at 30 degrees to the horizontal. You can see all of that information in the diagram. Particle P hangs below the pulley. P is on the plane and Q hangs below the pulley, so that the level of Q is 2 meters above the level of P. You can see in the diagram. P is released from rest. Okay, so that's the new information that's not given in the diagram. Slides down the plane. Okay, the plane is rough with coefficient of friction 0.2. Find the acceleration of P. Okay, the first part is fairly straightforward. This is just Newton's second law of motion. Represent all the forces that are acting on P and Q. On Q, you have the weight acting, that's 5 Newton. And in the upwards direction, you've got tension. And on P, you have the weight acting as well. That will be 25 Newton. There will be reaction. There will be tension in this direction. And there will be friction. P is moving down the plane, right? Slides down the plane. Yeah, so friction is going to be up the plane. This is the direction of friction. Okay, these are all the forces that are acting. Let's resolve weight, 25 Newton. It has one component acting in this direction and one in the other direction. If this angle is 30 degrees, we know that this angle here is also going to be 30 degrees. So this component is 25 cos 30, and the other component will be 25 sin 30. We have all these forces. So what do we do now? P is moving down the plane. So Q is moving up the plane. We apply Newton's second law of motion on both the particles one by one. Let's apply that on P. So the forward force is 25 sine 30. We're using resultant force equals mass into acceleration. What's the forward force? Forward force is 25 sine 30 because it's moving down the plane. Backward force is tension and also friction, 5 times acceleration. That's one equation that we have. Perpendicular to the surface, there's no movement, right? So these forces have to be equal to each other. R should equal 25 cos 30, right? Cos 30 is under root 3 over 2. So that becomes 25 under root 3 over 2. So R is equal to this, right? We just equate these two forces. R should equal 25 cos 30. So we have the value of R there. We can input that here now. 25 sine 30, that will be 25 into 0.5 minus tension minus friction. Friction can be written as mu times R. That equals 2.5 times A. 12.5 minus T, the value of coefficient of friction is 0.2 into R. R is 25 under root 3 over 2 equals 2.5 times A. This is one equation that we have. You can simplify this and see what that gives you. 12.5 minus 0.2 into 25 into under root 3 divided by 2. Let's just convert it to decimals. We don't want an exact answer anyway. So that's 8.16987. We can say that's 8.170 minus T equals 2.58. That's one equation. Okay. And then for Q as well, we apply Newton's second law of motion. Q is moving up the plane. Forward forces T, backward forces 5 equals mass of Q, which is 0.5 times acceleration. And you can see what that turns out to be. You can make T the subject here. What are we looking for? Acceleration, right? So let's eliminate T. So 5 plus 0.5 times A. Put that in the other equation. And that will give you 8.170 minus 5 plus 0.5 times A equals 2.5 times A. And you can find the value of acceleration from this. You can see what that turns out to be. 3.170 minus 0.5 times A equals 2.5A. And the value of A turns out to be 1 point something. What's this? 1.056 or 1.06? Thank you. 1.056. That's the more accurate number. Then we say A is equal to 3.17. That should be 0.57 or 0.56. 0.57, right? Yeah. And then that turns off to 1.06. That's the acceleration that we get. Okay. That's the first part. That was not that difficult. That's just the application of Newton's second law of motion. Okay. Let's look at the next part now. Use an energy method. What does that mean? Whenever it says energy method, that basically refers to this work energy principle. Work done by driving force is change in kinetic energy plus change in potential energy plus work done against resistance. Okay, that's what the energy method refers to. Okay, to find the speed of the particles at the instant when they are at the same vertical height. Okay, now these types of questions you will see more and more in recent papers when they talk about vertical height being equal to something or its difference being something. In your exam, what you would do would be you would always annotate with a pencil so that you can change that for the next part. Now, in the first part, we were talking about forces. So we resolved all the forces. So there was a lot of clutter in that diagram. So what I'm doing is I'm just copying that same diagram here again so that we can think of it. Again, now, you won't have enough time to keep drawing new diagrams. So annotate using a pencil so that for the next part, you can edit that if you need to. Okay, this is what the situation is. Now, we have already used the forces to find the value for acceleration. Okay, so let's forget about the forces for now. And let's focus on what they're talking about. So P is moving down the plane and Q is moving in the upwards direction. At some point, what happens is they have the same vertical height. What does that mean? That means if Q was, for instance, to come up by a certain distance, so let's say it comes here, then P is going to be at the same horizontal level, then P should be here. So if P comes here, then Q should have moved to this point, right? So that they have the same horizontal level. They have the same vertical height, right? The height is the same. They're at the same level like this. That's what they're saying. And now we have to use an energy method. What does that mean? Energy method. Let's write that down here on the side. Work done by the driving force, that is equal to change in kinetic energy plus the change in potential energy plus work done against resistance. Okay, let me write that down on the side. Work done by the driving force, that is equal to change in kinetic energy plus the change in potential energy plus work done against resistance. Okay, now how do we think about this? Work done by the driving force. Now, if we consider the whole system, on the whole system, there is no driving force as such, right? There's no external force that's making these particles move if we consider the whole system together. Okay, in that case, there's no driving force as such. If you were to consider P and Q separately, you could do that for Q. You could say tension is the driving force, but then for P, tension would be resistance. So they would basically balance out, right? On the left side, there will be tension into distance traveled. On the right side, there will be tension into distance traveled. They will cancel out. So we can ignore tension because when we consider the whole system, on the whole system, there is no driving force. Okay. So we have no driving force. What about the change in kinetic energy? How do we find that? Do we know the initial velocities? Initial velocities are 0, right? Initial velocities are 0 because they started from rest. What about the final velocities? That's what we have to find out. Find the speed of the particles when they are at the same height. So we have to find that final speed. So change in kinetic energy, we could say that could be written as, since they have different masses, we'd have to write them separately. Or we can add up their masses as well. That also works. The total mass of the system, what's that? That's 2.5 and 0.5, right? Since they're connected to each other, so their speeds are going to be the same, right? Whatever speed Q moves at, it should be the same speed that P moves at. So what's the total mass of the system? The total mass of the system is 2.5 plus 0.5. That's the mass into V squared minus U squared. What's the final speed? We don't know. Let's just call that V. Initial speed was 0. That's the change in kinetic energy. Okay, that's the change in kinetic energy. Okay, what next now? We also need change in potential energy. What about potential energy now? Now, potential energy cannot be calculated together because they are moving different distances vertically. Okay. So initial distance, between them in the vertical direction was 2 meters, right? It's not that they're meeting halfway there. It's not that it's Q is moving 1 meter up and P is moving 1 meter down. That's not what is happening, because Q is moving vertically, P is moving in this direction. So they will be moving different vertical distances. Now, what vertical distances are they traveling? That's the tricky part here. Okay, and that's the tricky part in such questions. You will find more of these in recent papers as well. How do we think about this? Let's suppose Q moves some distance vertically upwards. Let's suppose Q moves some distance and vertically upwards. Let's say that distance is X meters. It moves X meters in the upwards direction. Now, if Q moves X meters in the upwards direction, how much does P move down the plane? How much does P move down the plane? That also moves X distance down the plane, X meters down the plane, right? Because they're connected. Whatever is the distance that Q travels up, if this travels X units here, that's the same distance that P travels along the surface. That's also X. Can we find this value of X somehow? Until the point where when they reach the same vertical height, what we can do is we can make a right angle triangle like this. And that's what I can think of. That will be 30. Do we know anything in that triangle? Yeah. So what we can do is we can make a right angle triangle like this. We can make a right angle triangle like this. In this right angle triangle, you know the hypotenuse is X, right? This hypotenuse is X. What else? We know the angle. This angle is 30 degrees. Corresponding angles, this angle is 30 degrees, right? Can we say anything about this vertical distance? Can we say anything about this? The total is 2, right? The total is 2. We know that this lower part is X. What about this upper part? How much is this going to be? 2 minus X. So we have a right angle triangle. I'm going to draw that on the side now. We have this right angle triangle. I've enlarged that a bit, in which this is 30 degrees, hypotenuse is X, and this vertical distance is 2 minus X. Can we find the value of X from this? We can use trigonometry to find this value of X. Perpendicular and hypotenuse, we can use sine for that. Sine of 30, that equals sine of 30 equals perpendicular, which is 2 minus X over X. Sine 30 is 0.5. 0.5 equals 2 minus X over X. 0.5x equals 2 minus X. That will be 2 over 1.5. X turns out to be 4 over 3. That's the value of X that we're getting. That's the distance that Q travels vertically upwards. And that's the distance that P travels along the surface. Does that make sense? So Q is going 4 over 3 units up. Then what about the vertical distance that P is coming down? That's coming down 2 over 3, right? Because the total is 4 over 3. Q is moving up by 4 over 3. The total is 2. Q is going up by 4 over 3. P is going down by 2 over 3, right? So we found the change in their vertical heights. So can we find the change in potential energy now? Change in potential energy for Q. What would that be? mgh, mass of Q is 0.5 into g, which is 10, into height. Its height is increasing by x units, which is 4 over 3. Change in potential energy for P. P is going down. Mass of P is 2.5 into 10 into change in height. The height is decreasing. That means the potential energy is decreasing. So it has to be negative, because you could say change in height is negative. This is potential energy, this whole thing, right? So potential energy is this whole thing. This is kinetic energy, change in kinetic energy. All right. And then we have work done against resistance. What's the work done against resistance? We have friction, right? What's the value of friction? Do we know that? We found that here somewhere, I think. The value for friction, it was mu r, right? Mu into r. This was the value of friction. Let me write that down here. 0.2 into 25 under root 3 over 2. That was the value for friction. What's this value? Can somebody tell me what this value is in decimals? 2.5 under root 3, right? That's 4.3301. So this is 4.3301. That's the friction. That's a force, right? We are talking about work done against resistance. How much distance is traveled along the surface? How much distance is it traveling? X units, that's 4 over 3. We multiply by that. So this is friction times the distance traveled, which was X. Okay. And now you can find the value of V from this. You can see what that turns out to be. 3 over 2 V squared plus 5 into 4 divided by 3. That's 20 over 3. $50 over 3. And this, which is 5.7735. And you can find the value of V from this. And see what that turns out to be. What's the value of V that we get? Is that correct? 1.6785? 1.6786, and that rounds off to 1.68 meters per second. Let's look at question number 7 now. That's the next one that you asked about. A particle P of mass 0.2 kilograms. It is projected vertically upward from horizontal ground with speed 25 meters per second. Show that the speed of P when it reaches 20 meters above the ground is 50 meters per second. It's projected vertically upwards at 25 meters per second. What do we know about this? Since it's projected upwards, we'll take upwards positive. Initial velocity is 25. Displacement 20. What about acceleration? If you're taking upwards positive, gravity is acting downwards. So value of acceleration is negative 10. Find the final velocity, right? That's what we're looking for. What is the final velocity going to be? V squared equals U squared plus 2AS. And gives in this, V squared equals U, which is 20 for displacement, which is 20. 15. Okay, yeah. 15, that's the velocity that you get. Now it could plus 15, negative 15, since we're looking for speed, we just take the positive value, right? The speed can not be negative. So value B is 15. Okay, that's the first part, fairly straightforward. Let's move on to the next one now. When P reaches 20 meters above the ground, it collides with a second particle Q of mass 0.1 kilograms, which is moving downwards at 20 meters per second. P is brought to instantaneous rest in this collision. Find the velocity of Q immediately after this collision. Again, the difficult type of question, kinematics and momentum, both of them together. Let's see how to deal with this now. Okay. When P reaches 20 meters above the ground, let's represent that here. Let's say this is the horizontal ground. The particle P was projected vertically upwards in this direction. Its initial velocity was 20 meters. No, its initial velocity was what? 25 meters per second. Although that doesn't matter. Let's just focus on that part when it collides. So let's just forget about this. Let's say P was here and Q was also here. Q is moving downwards at 20 meters per second and P was moving upwards at 15 meters per second. P is brought to instantaneous rest in this collision. Find the velocity of Q immediately after the collision. Okay, let's use conservation of momentum and see what that gives us. Momentum before collision should equal momentum after collision. What's the mass? Mass of P was 0.2 kilograms. Mass of Q 0.1 kilogram. We have to take one direction positive. We have a direction for both objects. If we take upwards positive, then what's the momentum before collision? We're taking upwards positive, right? So for P, mass is 0.2, velocity is 15. For Q, mass is 0.1, and velocity is minus 20. That equals momentum after collision. Velocity of P after collision is just 0. So its momentum is also 0, right? If you can do 0.2 into 0, because it says P is brought to instantaneous rest in this collision. What's the velocity of Q? That's 0.1 times VQ. That will give you the value of VQ. You can see what that is. This is going to be 3 minus 2. That equals 0.1 VQ. And VQ turns out to be 10 meters per second from here. Is that okay? Okay, good. Let's move on. That was part B, pretty straightforward. Because of the speed that it had immediately before hitting the ground, find the height above the ground at which P and Q next collide. Okay, P reaches the ground, it rebounds back directly upwards with half the speed that it had immediately before hitting the ground. Find the height above the ground which P and Q next collide. Okay, that's fairly complicated. Okay, let's think about this. So we have the ground level somewhere. And what's happening is, think about the point of collision, first of all. Do we know where collision happens? It happens 20 meters above the ground. So we know the starting point. The collision happens 20 meters above the ground. Collision is happening. We have particle Q here, which immediately after collision goes 10 meters per second in the upwards direction, right? That's what we found in the previous part. It starts going 10 meters at 10 meters per second in the upwards direction. And P, it starts going downwards, but it starts from rest, 0 meter per second. Its velocity was 0 meter per second. Now what happens is P hits the ground, right? P hits the ground and it rebounds at half the speed that it had immediately before hitting the ground. Yes, Q is moving up because we found the velocity of Q and that turned out to be positive. That means it's going upwards direction, in the upwards direction. Okay, now, since P is moving downwards, let's first find out the velocity at which it hits the ground. How do you find that? P is moving downwards, we take downwards positive for P. Let's write that down here. Downwards direction, we're taking positive. We know the initial velocity. Initial velocity is 0. We know the final velocity. No, we don't know that. We have to find that. We know acceleration is moving downwards. We're taking downwards positive. So acceleration would be positive 10. We know displacement is 20. And we have to find the final velocity at which it hits the ground. What would that be? V equals U square. No, V square equals U square plus 2AS. Let's input values in this and see what that is. 20, right? So P hits the ground at 20 meters per second. Velocity at which P hits the ground. Okay. Now it says P rebounds with half the speed that it had immediately before hitting. So now what's happening is ten meters per second hits the ground. Let me show the second part of this on the right side now. Second part of the journey. So this was the first part of the journey on the left side. Let me try and color code this somehow. This was the first part of the journey. Okay, now what about the second part of the journey? P is now moving upwards, and P is moving at 10 meters per second. And now, when P was, but it's a standard that you need to know about. Object is moving in only one direction, you take the positive from it. So if it's only one direction motion, whichever direction it's moving in, you take that direction positive. If the direction is changing during motion, if an object is traveling in one direction and it's also going throughout the journey, you take upwards positive, downwards negative. Okay, if it's also changing that. For the first part of the journey, only considering how P is moving upwards. So now we take upwards positive of P. Okay. Remember, Q's height is not going to be 20 meters. He was going downwards as well, right? How much Q had no upwards at 10 meters per second, not zero. That was for P. P was going downwards at zero. Now let's see what has happened to Q in the meantime. Now for that, we will need the time taken for P to hit the ground. How much time did P take to hit the ground? Let's find that first of all. V equals U plus AT. Final velocity was 20 equals U, that's 0, plus 10 times T. So the time that P took to hit the ground was 0.5 seconds. Okay. So P hit the ground in 0.5 seconds. Now in that time, Q would have already moved somewhere. Let's think about that now. How much did Q move? This was for P, right? What about Q? What was happening to Q at the same time? Direction after collision. So for Q, what I'm going to do is I'm going to take upwards direction as positive. Its initial velocity was 10. Acceleration, since gravity is acting downwards. Gravity is acting downwards. And Q, we are taking upwards positive. Acceleration is negative 10. What else do we know? We know the time taken now. Time is 0.5. Let's see what we get from this. Yeah, T is 2. I'm sorry. That's 2. 20 over 10. That should have been 2 here. Thank you for pointing that out. Time is 2 here, not 0.5. Okay, so what about the displacement of Q in these 2 seconds while P was moving downwards? Let's find that out. Let's find both of them, displacement and final velocity. We might need the final velocity as well. Let's see. So S equals what? UT plus half AT square. U is 10 into time, that is 2, plus 1 over 2 into minus 10 into 2 squared. What do we get from this? 20 minus 5 into 4, is that 0? Is that turning out to be 0? That's 0, right? Yeah, okay. So this is 0. So displacement turns out to be 0. What that means is so it's still, so now Q is starting its journey from here. But now, since it's moving in the downward direction, its downward velocity now is 10 meters per second, right? When it reaches the same point again, its speed is again going to be 10 meters per second. If you want to confirm that, you can do that. Time. What was that? 10 meters per second. After 2 seconds is 10 meters per second in the downward direction. So that is what is happening now. Q is above the ground. And now we have to figure out at what point they collide with each other. Any problems until this point? Any problems until this point? Okay, so that's a good question. after I say journey, yes, that's the general rule that we have. For one object, we should keep the same direction positive throughout the journey. For each object, we keep the same direction positive throughout the journey. Now, that is true when an object is moving like this. For example, P is going upwards and then it goes downwards. We say we take upwards positive throughout the journey. Doesn't matter whether it's moving upward, right? That's correct. But here, we are not considering collision happening. P is hitting the ground. P is hitting the ground. We cannot consider one single equation for the whole journey now because there's a collision that's happening in the middle. Right? P was going downwards earlier. Because when it collides with the ground, everything changes at that point, right? So we cannot consider these two parts together while P is moving downwards and while P is separately. While P is moving downwards, that's a totally separate thing. So for that, what we do is we take downwards positive. But then after its collision, it's starting a new journey now. Okay, it's starting a new journey. So now for its second part of the journey, now we can say upward direction is positive. If there was no collision, and then you should consider, okay? But in this case, since there's collision, we are considering them separately. That's why we are changing the positive direction. Now, as long as you are consistent, mathematically, it actually does not matter which direction you take positive. So as long as you stay consistent, both directions positive, as long as you do everything according to that, they will work. But if you don't follow that rule that you're talking about, then things become a bit counterintuitive and it becomes difficult to do that. That's why we have this thumb rule that we'll always do it like this, that if a particle is moving in the upward direction, we take that positive. If it's moving in the downward direction, we take that positive. If it's two-way motion, we say upwards is positive, downwards is negative. If it's horizontal two-way motion, we say right positive, left negative. Okay. Yes, you're saying something? No? Okay, all right. So now we've reached this point when Q is now moving in the downward direction. Now we're moving in the downward direction. About the direction. So about the direction, I was saying, since there's a collision happening, P is colliding with the ground. So the part before collision, that's completely separate from the part after collision. So that is why before collision, we treat that as a separate journey. Since P is moving downwards, we take downwards positive for that. After collision, this is a separate journey because you see its speed has also changed now. For this, we consider upwards positive. If there was no collision, then yes, that's what we generally do, that we consider the same direction positive for one object throughout the journey. We don't change that in the middle. Okay, but in this case, we're changing because these are two separate journeys because of the collision that's happening. Is that okay? Yes, displacement of Q was 0, so it is 20 meters above the ground because that's where it was initially. If displacement is 0, that means it has come back to the same point again. All right, so its height is 20 meters. Now, once you reach this point, the rest is not that difficult after this because now P is projected from the ground. It's moving in the upwards direction. We consider upwards positive for that. Q is moving in the downward direction. We consider downwards positive for that. What do we know about P? We know initial velocity is 10. We know acceleration is -10. And do we know anything else? No. What about Q? We know the initial velocity is 10. We know the acceleration is positive 10 because the downward direction is positive. Now, at some point, they collide again. Let's call that point something. Let's say this point is X. Now, these are two things that we know for both of them, right? Initial velocity and acceleration. What is it that we do not know? We do not know final velocity, we do not know time, and we do not know displacement. Is there anything common between them that we can use here? Time is common, right? Time is common because they start at the same point and they're ending at the same point. So time is common. That's another variable that we should be using here. We can say if time for P is T, then the time for Q is also T. Is there anything else that we can connect? Yes. So for P, upwards displacement is SP. For Q, the displacement is SQ until that point. We know that this total has to be 20. That means SP plus SQ, therefore, that should equal 20. And that is going to give us the time until collision. Yes. Okay. Let's input values in this now. S equals ut plus half at square. So for P, it will be 10 into T, which is T, plus half into A, which is minus 10 into T squared, plus U, which is 10 into T, plus 1 over 2 into 10 into T squared. That equals 20. Now, this and this, they get cancelled. And we're left with 20T equals 20, and the time turns out to be 1. So collision happens after of collision of P with ground, right? So 1 second, it takes 1 second to reach that point. We wanted the height at which the collision happens. What's the height? SP equals ut plus half at squared. That's n times plus 1 over 2, which is 1 squared. What do we get from this? 10 minus 5, and that's 5 meters. This is where the collision happens. That's what you wanted to find out. Make sense? Having seen questions like these before, kinematics and momentum, this was actually one of the easier ones of them. The diagram shows a track ABCD, which lies in a vertical plane. The section AB is a straight line inclined at an angle of 30 degrees to the horizontal and is smooth. AB is smooth, okay. BC is a horizontal straight line, and that's rough. CD is also rough. Lengths are given, they're all 2 meters. A particle is released from rest at the point A. The coefficient of friction between the particle and both BC and CD is mu. There's no change in the speed of the particle when it passes through either of the points B and C. You're given the value for mu. Find the distance with which the particle has moved up the section CD when its speed is 1 meter per second. Okay, so we've got different parts in this journey. We've got A to B part, and then B to C, and then C to some point. What's happening is the particle is going to come down here, and then it'll move on the surface BC, and then they're saying at some point on the section CD, the speed becomes 1 meter per second. We have to find the distance traveled on the CD part when its distance becomes 1 meter per second. Let's say this is that point. Now let's see what happens from A to B first of all. From A to this, what do we know about this part of the journey? We know the initial velocity, RT. It's released from rest. Okay, so U is equal to 0. Anything else? We know that displacement is 2 meters. What would be the final velocity? Yeah, we don't. But the acceleration for this part from A to B. It's a smooth surface. It's a smooth surface. And apart from weight, there's nothing else that is acting. Right? Apart from weight, there's nothing else that's acting. So we can say the acceleration, therefore, is going to be 10 sine theta. Right? We know that. If it's a smooth inclined surface with weight as the only force along motion, acceleration is given by 10 sine theta. All right. So what's the value of theta? Do we know that? 30. So it's going to be 10 sine 30. And this turns out to be 5. Acceleration is 5. So initial velocity is 0. Displacement is 2. The final velocity is what we have to figure out. Can we find the final velocity? V square equals U square plus 2AS. What do we get from this? U is 0. Plus 2 into A, which is 5, into S, which is 2. And that will give us something. Square root of 20. That's the velocity at the point B. That's one thing that we were looking for. Let's save some space. How much effort do we have? Not much. This is what happens from A to B. What about B to C part of the journey? What happens in that part? Let's think about that now. B to C. Now the velocity at B is square root of 20. So we know do not have acceleration, but can we find that? We're given the value for mu. What are the forces acting on the particle? In the forward direction, there's no force. There's only backward force. That's friction. And friction is equal to mu times R. What's the value of R? The weight is, do we know that? Okay, so there's no weight that is given. So we'll have to write it in terms of M. So let's say this is 10M. Then upwards reaction would be 10M as well, right? Because vertically there are no forces that So what about friction now? Motion, force, elevation. Can we find the final velocity for this part now? V is equal to u square plus 2as again. What does that give us? Square root of 20 whole squared plus 2 into minus 1 into displacement, that is 2. 20 minus 20 minus 4, that's 16, and that turns out to be 4 meters per second. This is the velocity of the particle at the point C now. This is 4 meters per second. So at the bottom of that hill, the velocity is given to be 4 meters per second. Is this finite? That's the velocity at the bottom of the hill. Now we consider this part of the journey from C on. What about this part of the journey now, from C to X? Let's consider that. From C to X now. We know the initial velocity, that is 4. We know the final velocity, that is distance traveled. We can use Newton's second law of motion in this part as well. There's no forward force, there's only friction that as well, because it's an inclined surface. Vertically downwards, we've got a weight of 10 times m. There's one component acting for 10m into sine 10m into cos theta, this component, and the other component would be 10m sine theta. And there's going to be reaction that acts in this direction. These are all the forces that are acting on this particle on the inclined surface. All right, so we've got reaction that should equal 10m cos theta. Along the surface, we've got friction and this weight component. All right. So now, for C to X part, we can say, number one, reaction equals 10m into cos of theta. Newton law of motion, it's moving up the plane. So there's no forward force, that will be 0. We can say resultant force equals mass into acceleration. Forward force is 0 minus friction and also a component of weight. That's sine theta. That equals mass into x. We have sine theta given. The angle is 30, in fact. So we can just use that here. 10m into cos of 30 minus 10 into sine of this cancelled out, right? M is appearing in every simulator. So you get a value for acceleration from this. You can see what that is. Minus 0.1 into 10 cos of 30 minus 10 over 2, which is 5. Acceleration that would be minus, confirm this. Initial velocity and final velocity, what is it that we're looking for? We're looking for displacement. We'll check equation do we use now? V squared equals u squared plus 2 minus 15 divided by minus 2 into 5.86. So 1.28 meters, that's the simple subdivision. Okay. Yes, it is long, it is lengthy. The last question you'll find in most M1 papers, they're pretty lengthy. So you do have time management problems in M1. You can only improve this with a lot of practice. And then just make sure that you do the questions that you know first, so that even if you end up losing some marks here, the threshold takes care of it. Now it says it's given instead that with a different value of mu, the particle travels 1 meter up the track from C before it comes instantaneously to rest. Find the value of mu and the speed of the particle at the instant that it passes C for the second time. Okay, let's think about this now. So now the value for mu is not the same as before. That has changed. And we don't know what that is. Okay, so now the only thing that's changing is the value for mu, right? The value for mu is changing. That means for the first part of the journey, from A to B, everything is the same as before, right? So at B, the speed is going to be the same as before, which was under root 20. So from A to B, nothing changes. This is still square root of 20 meter per second at this point. Now, what happens from B to C now? Let's think about that. From B to C, this is what we did earlier, right? Just copy that here. This is what we did for B to C part earlier. We can use the same equation again. This is what we did there. Now let's just edit this a bit. Initial velocity is still square root of 20. Displacement was 2. Resultant force equals mass into acceleration minus friction equals mass into acceleration. The only thing that changes now is we don't know that the value of mu is 0.1, so we just use mu here. Okay, so we just use mu into r, which was what was the value for r? 10 times m. That equals mass into acceleration, and that gives us a equal to minus 10 mu. That's the acceleration for the second part of the journey. Okay, so this is no longer valid now. That's B to C part. Now we consider that again. Let's think about C to D part, because for that, now we have more information. We know that the particle travels 1 meter up the track and its final velocity is 0. So that's what we know about the last part of the journey. So we can use the last part now because we have more information for the last part. For C to D part, let's see what information we've got for that. For not C to D, it's this point, let's call this point x, from C to x, we know that the displacement is 1 meter, right? We know that. We know that what else do we know? Final velocity is 0, right? At this point, the velocity is 0. And is there anything else that we do not have? Can you find acceleration somehow for this part of the journey now? That will also be in terms of A. Then we can use the initial velocity for that part. And why is it only 4 marks? Okay, now from the B to C part of the journey, let's just see what information we already have. Let's try to find final velocity in terms of mu and see what that turns out to be. Then we can use that there. U square plus 2 times A. That's V square, right? 20 minus 40 mu. And then we would be minus 40 mu at the point C. Now we could use that as the initial velocity here. That is 40 mu. Acceleration for this part of the journey. Acceleration for this part of the journey, again, we can use the same thing that we did earlier for this. They give us. Okay, I'm trying to find the acceleration now. Diagram. The only thing that changes here is the value for mu now. Okay, so we'll not input mu equal to 0.1 anymore. We'll keep this in front in terms of mu. So this becomes mu. And then minus mu into 10m cos 30. And we're left with A equal to minus cos strength. And now we can connect these things to find the value for mu now. That's very unfair. It's only 4 marks. Let's see what this turns out to be now. A is now this. So which equation connects these 4 things? A, U, S, and V. We can use V square equals U square plus 2AS. Right? Do not mix up this mu and U. These are different. So V is 0. U squared is 20 minus 40 mu to 3 times mu minus 5 equals s into s. That's just 1. Now we can solve this to find the value for mu and see what that turns out to be. Root 3 mu minus 5. Sorry, minus 10 equals 0. And that will give us the value for mu. You can see what that turns out to be. It's going to be 10 divided by 40 plus 10 under root 3. And that turns out to be 0. 11745. That's the value of mu that I'm getting. 0.174. Can somebody confirm this calculation? That's okay, right? Okay, so that's mu now. And once we've got the value for mu, they also want us to find the speed of the particle at the instant that it passes c for the second time. So now x reaches this point x, and now when it comes to rest, it goes down again towards c. What's the speed at which it passes the point c now? That's what we need to figure out. So now we're going back from x to c. What do we know about this part of the journey now? From x to c now, we can consider the downward direction positive, right? What's the initial velocity? It started from rest. The displacement is 1. Acceleration is going to remain the same as before. That's not going to change because it's the same surface, right? It's the same surface. We've got the same forces acting. It's the same forces acting, right? But we're taking downwards positive. So the acceleration value is going to be positive now. That will be 5 under root 3 mu plus 5. And that's the value of acceleration. The same as before, we just take positive now because earlier we were taking upwards positive, now we're taking downwards positive. Right, so earlier we were considering this direction positive. Now we're considering this direction positive. Okay, now we have the value for mu. We can input that here, 5 under root 3 into 0.17446 plus 5. And that will give you the value for acceleration. You can see what that turns out to be. 5 under root 3 times 0.17446 plus 5. And that gives you 6.51. 6.511. You got the acceleration as well. Now find the speed, final speed. So we can use v squared equals u squared plus 2as for this now. V squared equals 0 squared plus 2 into 6.511 times displacement, that is 1. And that will give you the value for velocity, finally, that you're looking for. 2 into 6.511, square root of that. And that turns out to be 3.61. That's the velocity at which the particle passes through C the second time. Is that what you're getting? Can somebody confirm this? Yeah, this is a real question. Can somebody check the working again? Oh. Friction is going to act opposite. Weight was, oh, I'm sorry. I'm sorry, this is not correct. This is not correct. This is not correct. Acceleration. We'll have to calculate that again. We can't use that same value because of the weight component as well, right? Because weight is now acting down the plane, friction is acting there. Yeah, I'm sorry. Acceleration is not correct here. We'll have to calculate that again, actually. The reason for that is, while it's going down, this is not going to be the same. While it's going down, Weight is the forward direction now, right? It was the backward direction earlier. Weight component, this would be 10m sine theta, the weight component, and in the backward direction there'll be friction. This will be friction. So we'll have to calculate this again. 10m sine theta minus friction, that equals mass into acceleration. We'd have to do this again. Okay. So 10m sine theta, what did that turn out to be? That was 5 times m minus friction. Friction was 5 under root 3 times mu times m equals mass into acceleration. The value of A actually turns out to be 5 minus 5 under root 3. Right? 5 minus 5 under root 3. Because now it's moving down the plane. Okay. Mu, 5 under root 3 times mu. Now you can input the value for mu in this. You can input the value for mu in this. Input the value for mu. And that gives you 5 minus 5 under root 3 times mu value for acceleration. That will be something 5 minus 5 under root 3 times 0.17446. Acceleration turns out to be 3.4. Nine, you input this value there now. We 2 into this and then square root of that. And that's 2.64. That is what we were looking for. That's the final velocity that we get. Okay. So we had to find acceleration again as well. That's all that we've got to do this for these 4 marks, right? Not that difficult, fairly straightforward. Just little amount of working and get the result, right? Difficult because we had 5 fairly easy questions until now. Okay. Now it says a car of mass 1800 kilograms is towing a trailer of mass 300 kg up a straight road, inclined at an angle alpha to the horizontal, where sine alpha is 0.05. The car and trailer are connected by a tow bar, which is right to rigid, it's back to the road. There is a resistance force acting on the car, and resistance force on that. Driving force is this. It's given that F equals 100. Find the acceleration and the tension. Okay. So we have an inclined surface. We have an inclined surface. Let's say it looks like this. The angle of the surface is alpha, and we're given the value of sine alpha here. Mass is given. This is given. This is mass of car. This is mass of trailer. Resistance 800 on the car and F on the trailer. Driving forces 3000 Newton. F was resistance, that's given to be 100. Okay, now let's represent this. Car is towing the trailer up the road. So what's going to be ahead? Car is going to be here and trailer is going to be behind that because car is towing the trailer, right? So this is the trailer and they're connected by a tow bar. They're connected like this. Okay, now we are looking for acceleration and tension. When in the question they ask about tension and acceleration, that's a very clear hint that we have to use Newton's second law of motion, right? Tension is a force, acceleration, what connects forces and acceleration? It's Newton's second law of motion. That's what we will use. Let's apply Newton's second law of motion, both the objects one by one. Okay, so we'll talk about that. Let's represent all the forces. Let's represent all the forces first, and then we'll have a look at that. What are the forces acting on the car? We've got weight of the car that acts vertically downwards. What I'll do is I'll represent them with different colors so they don't mix up. This is the trailer. Okay, weight of car that is 18,000 Newton. Now you see, we're not talking about friction anywhere. We're talking about resistance. So we don't really need to use normal reactions anywhere, right? There is going to be normal reaction on the car. There is going to be normal reaction on the trailer as well. But we don't need to use them in our calculations anywhere as such, right? So we can ignore them if we want, and that's okay, because we don't have friction involved here. So we have weight. What else? We have driving force on the car. That's what it says. Driving force is 3,000 Newton. That's acting in this direction. What else? There's resistance on the car, and that is 800 Newton. That will act opposite to the motion. Let's represent it here. That is 800 Newton. And there's going to be tension because it's connected to the tow bar. This is tension that also acts away from car. That's towards the left side. These are the forces acting on the car. What about the trailer now? What about the forces acting on the trailer? What are they going to be? Forces acting on the trailer. It's going to be weight of the trailer. It acts vertically downwards, which is 3,000 Newton, because the mass is 300. Tension away from the trailer, that acts in this direction. Friction, we know that the value, resistance, we know the value of that in the first part is given to be 100 Newton. This is 100. And that's it. We have normal reaction, but we don't need to represent that. These are the forces that are acting on the trailer. Okay, now the question is, does the driving force only act on the car, or does it also act on the trailer? The question says, the driving force of the car's engine is 3,000, right? So it's only for the car. That's 3,000. For the trailer, the driving force is this tension. Tension is what is driving the trailer forward, right? So the driving force is pushing the car forward in this direction. Because of that, you have this tension in the tow bar, and that tension acts as the driving force for the trailer. Okay. The trailer is being towed in the first place because its engine is not working, right? That's why it's being towed like this. So it does not have a driving force of its own as such. It's the tension. Now what we do is we apply Newton's second law of motion on both the objects one by one. For that, we also have to resolve the weight first of all. This is 18,000. The angle of inclination of the plane is alpha. So let's say this angle is alpha. The component of weight of trailer in this direction, that's going to be 3,000 into sine of alpha, because this is the angle alpha, right? There's going to be one component here as well, but we don't need that. Let's just ignore that. We have two components for weight as well, one in this direction, one in this direction. If this is alpha, we know that this angle is also alpha. So this component is going to be 18,000 sine alpha. The other is going to be cos alpha. Again, we don't need that. That would be equal to the normal reaction, right? If we had friction involved, then we would use that as well. In this case, we have no friction involved, so we don't need to use the perpendicular component of weight as such. Makes sense? So now we've got all of these forces that are acting. We apply Newton's second law of motion on both of them one by one. So we've got the car and we've got the trailer. Car and the trailer. Now for the car, since the forward direction is this, for both of them, this is the forward direction, we say resultant force equals mass into acceleration. That's the formula that we've got, Newton's second law of motion. Forward force minus the backward force. What's the forward force for the car? That's 3,000. We'll just highlight them. 3000. Backwards is 800 T and this weight. For the trailer, the forward force is T, backwards is 100, 3000 sine alpha. Okay. So forward force for the car, that's 3000 minus the backward forces, T, 800 and 18,000. Sine of alpha. This should equal mass of the car, which is 1800 times acceleration. This is one equation that we've got. And then we make another equation for the trailer. What would that be? For the trailer, the forward force is T, backward forces are 100 and 3000 sine of alpha. That equals mass of the trailer, which is 300 times acceleration. These are the two equations that we get from this. We solve them simultaneously, and that's going to give us the result. We are given that sine alpha is 0.05. We can input that here. So it becomes 3000 minus T minus 800. 3000 minus 800, what's that? That's 2200 minus T minus 18,000 into 0.05. That's the value of sine alpha, equals 1800 times A. What's this value on the left side? 2200 minus 18,000 times 0.05. 1300 minus T, that equals 1800 times A. Okay. Now, what about the other one? T minus 100 minus 3000 into sine of alpha, that's 0.05, equals 300 times acceleration, and that gives us T minus 250 equals 300 times acceleration. These are two equations that we get. From the first one, we can say T is equal to 1300 plus 1800 A. From the second one, we get T equal to 250 plus 300 times A. We equate them. No, this is minus 1300 minus 1800 A. 1300 minus 1800 A, that equals 250 plus 300 times A, and that gives us 2100 A equal to 1050, and A equals 0.5 meters per second square. That's the acceleration that we were looking for. Put that back in any one of those two equations, and we'll get the value of corresponding tension as well. 1300 minus 1800 into 0.5, and that will be 1300 minus 900. That's 400. The value of tension turns out to be 400. That's what we have to do in this part. That's a standard Newton's second law of motion question. A lot of careless errors happen in questions like these. A lot of people end up forgetting one of these forces. Mostly, one of these forces is what people end up forgetting. So be careful. Otherwise, this question is not that difficult as well. It just requires a lot of calculation, and you need to avoid careless errors in that. Okay, that was part A of this. Now it says it's given instead that the total work done, the tension is equal because the things connecting them are still intact. It's the same string. It's one single string, right? And it's applying some force on the car there, some force on the trailer. It has to be equal. If it's different, then the string would no longer be taut. Yes, you're right. Otherwise, it would either not be taut or it would break. One of those two things would happen, right? No, Newton's second law of motion, Newton's third law. Okay, yeah. So if you consider the forces acting on the string, they have to be equal on both sides. Yeah, so that's what Newton's third law of motion says. Since the string is kind of in equilibrium, right? With respect to the other two objects. Okay, now it's given instead that the total work done against F in moving a distance of 50 meters up the road is 6,000 joules. The speed of the car at the start of the 50 meters is 20 meters per second. Use an energy method to find the speed of the car at the end of the 50 meters. Okay, now whenever they say energy method, what they mean is the work energy principle that looks like this: work done by the driving force that is equal to change in kinetic energy plus the change in potential energy plus work done against resistance. Now, some of you would have done some variation of this. You would be used to writing it some different way. That's perfectly okay. So there are a number of different ways of writing this. Okay, this is the way that I generally use. Work done by driving force that equals change in kinetic energy plus change in potential energy plus work done against resistance. That's what we have to use. Okay, now what we can do is we can just copy that diagram here. Copy this diagram. Okay, so now we've got to use an energy method. We can get rid of these forces, the components. We don't need them anymore. We have found the value of acceleration already. That's 0.5. That's one thing that we know already. And we know the value for tension as well. Let's just remove these forces so that we reduce the clutter a bit. And then we'll think about it. Then if we need to represent any force again, we can do that. But for now, let's just get rid of them. Okay, so this is what the situation looks like. It's given instead. Now, that basically tells you there was some information given in the first part that's no longer relevant. So in the first part, it said that F is equal to 100. So now F is not equal to 100. Oh, F is not equal to 100. That also means that acceleration and tension, they're also not the same. Okay, so sorry about that. You cannot use the values of acceleration and tension because that was based on the value of F being 100. Okay, now that this value is not 100, nothing in the first part is relevant anymore. Okay, only this information is valid that was given in the question itself. Okay, now the total work done against F. So what were the forces acting? What were the resistive forces acting on the car? The resistance was 800, right? And on the trailer, it was F. They are saying the total work done against F in moving a distance of 50 meters up the road is 6,000 joules. Work done against this resistance, that is given to be 6,000 joules. Now, let's just stop there. Can we find the value of F from that? We are given work done and we're given the distance traveled, 50 meters. Work is F into D, right? Work done against resistance, if we had to find that, we would say work done against resistance is 6,000. That equals F, and that is done again for a distance of 50 meters. The value of F, that will turn out to be 6,000 over 50, which is 1,200 or 120? 120. 120 Newton. That's the value of F that we get. Okay, that's the value of resistance. Now that we've got this value, what else is given? The speed of the car at the start of the 50 meters is 20 meters per second. So the car is moving up. When it started its journey, its speed at this point was 20 meters per second. This speed was 20 meters per second. It's traveling up a distance of 50 meters. Now, both of these objects are traveling together, right? The car is moving and the trailer is also moving. Start is from 20 meters per second. Now, we have to use this energy method to find the speed of the car at the end of the 50 meters. So let's say this is the 50 meters journey. At the end, at this point, what is the speed? That is what we are looking for. Now, remember this car and the trailer, they're connected to each other. So whatever speed the car is moving at, the trailer would be moving at the same speed as well. Okay, the trailer would also be moving at the same speed. Now that we understand that, let's input values in this formula. Work done by the driving force. What was the driving force? Driving force was given to be 3000 Newton. We are considering the whole system now. Okay, so in energy questions like this, you think of the whole system like this. That makes things easier. You can consider them separately as well, but that will make things very confusing. I would recommend that you consider the whole thing together. On this whole thing, what's the driving force? 3000. What's the work done by the driving force? What's the work done by the driving force going to be? Multiply the force by the distance traveled. That's 50 meters. So 3000 times 50. That's the work done by the driving force. What about the change in kinetic energy? Change in kinetic energy. Change in kinetic energy, that's given by half into m into v square minus u square. What's the mass? What's the mass? Total mass of the system. 1800 plus 300, that becomes 2100. So 1/2 into 2100 into v square minus u square. Final speed is v, that's v squared, minus u squared. Initial velocity, that was 20, so minus 20 squared. That's the change in kinetic energy, right? This is what I've written here. What about the change in potential energy now? What about the change in potential energy? Potential energy is mg into change in height, right? What's the total mass? Change in height is going to be the same for both of them. So we can do that together as well. Whatever is the change in height for the car, it's going to be the same for the trailer as well. M, the total mass is 2100 into g, that is 10, into change in height. Now, how much is the height changing? We don't know that, right? Can we find that somehow? The change in height. Let's make a triangle like this. It's traveling a distance of 50 meters. The angle of inclination of the plane is alpha. Angle of inclination of the plane is alpha. अभी तो brain के process करने का time, अभी तो मुश्किल questions आए हैं. So we have around 25-30 minutes more. Okay, so try to pay attention. These are important questions now. 50 और ये आपका hypotenuse था. This is the hypotenuse, and now what you have to do is, okay, I lost my train of thought. So we had this hypotenuse and we have this angle. What were we going to do? Yeah, we were looking for height. We wanted to find potential energy, right? Change in potential energy. So let's call this h. Can we find that now? Perpendicular over hypotenuse, that's h over 50. That equals sine of alpha. Now the question told us the value of sine alpha, that was 0.05. And that is give us the value of h, that's 50 sine alpha, which you can see what that turns out to be. 50 into 0.05. What's this value? 2.5. Okay, thank you. This is 2.5. That's the change in height. Is the height increasing or decreasing? Is the height increasing or decreasing? The height is increasing, right? So we use this as a positive number. Plus work done against resistance. What about that? The total work done against F in moving a distance of 50 meters up the road is 6,000 joules. So we know the work done against F already. This is something that we do know already. Okay, that is 6,000. But there's also work done against the other resistance. What's the other resistance? Resistance on the car, that's 800. What would that be? Resistive force is 800 multiplied by the distance traveled, which is 50. That's the equation that you get. You solve this equation, and that's going to give you the value for V. Okay, let's do that. 3,000 into 50. What would that be? 15 and then 4 zeros, 150,000 plus you can see whatever this value turns out to be, 1050 v² minus 400 into 2100 divided by 2, that's 420,000 plus 21,000 times 2.5, that's 525,000 plus 6,000 plus 800 times 50, that would be 40,000. And now you can find the value of v from this, or where was the equation sign? This was an equation sign. And now you can find the value of v from this. You can see what that turns out to be. 150,000. From where did we get 2100? That's the total mass. Since we're considering the whole system, one mass is 1800, the other is 300. So the total mass is 2100. Okay, so this 2100 is coming from 300 kg plus 1800 kg. That's 2100 kilograms, mass of the whole system. 6,000 is this work done against resistance. Work done against resistance of F. This resistance. That was given in the question already, so we just use that as it is. So this whole thing is the work done against resistance. And this was the change in potential energy. And this was the change in kinetic energy. Okay. Now you can see what the value of V turns out to be from here. 150,000 plus 420,000 minus 52,500 minus 6,000 minus 40,000 divided by 1050, square root of that, 21.19. Can somebody confirm this? Is that what we get? Round this off to three significant figures, 21.2 meters per second, and that's your final answer. That's the final speed that we were looking for. Make sense? Yeah, thank you. 21.19. Yeah, okay, good. That was 6 part B. This was slightly tricky, right? Above average difficulty, I would say. Work done against resistance. So there are two resistances, right? There are two resistances. One is this. Okay, one is this. We already know the work done against resistance. That's 6,000. If you want to do this again, you can do that. You can say it's F. We found that value 120. Okay, it turned out we did not really use that anywhere, but you could do 120 in 250, and that's the 6,000. Okay. For the other one, this is 800 resistance. We multiply that by the resistance traveled 50. That's the other resistance. So one resistance was already given. I just used that, and the other I found like this by multiplying that resistance value with the distance. Is that okay? All right. Let's move on to the next one now. Now, this, as I said, looked like a fairly difficult question. Let's see what it says now, because it looks like it's a combination of kinematics and momentum, and this is always a deadly combination. When they combine questions on kinematics and momentum, they end up being very long and very, very difficult. Let's see what this is about. The other one is for the car. Yes, one is for the trailer, the other is for the car. Yes. So this is for the trailer. This is for the car. Okay. Okay, now let's have a look at this. The diagram shows two particles P and Q which lie on a line of greatest slope of a plane ABC. Now you see, the first 5-6 questions were fairly straightforward, and what happened was we got relaxed while we were doing those questions, and we thought, okay, we're almost done. We just have like 2 questions left. But if you end up doing that in an exam situation, you find easy questions and then you think, okay, there's a lot of time left and we're almost done, then you can sometimes end up getting something like this at the end. So make sure that you skim through the paper once so that you know what's coming next. Okay, so you don't get relaxed too early. So you keep your speed fine, otherwise it will be difficult. I don't recommend that you do harder questions first, because if you start doing this first, you will end up spending 30 minutes on this, and then you'll be panicking that you don't have enough time left, and you will end up doing the easier questions wrong as well. Okay, do the paper so skim through the paper first of all, so you have an idea of what's coming at what point. Go in order, do the questions that you can easily figure out in the first go through the whole paper like that, and then you come back to the start again, try the questions that you skipped, and then questions like these should definitely be left for the end. However, you should leave enough time for these as well. Okay, so you will need enough time for this, otherwise it will be very hard to figure this out. Okay, so you need to make sure you keep the harder questions for the end, but also leave enough time for them. Okay, doing harder questions first is not a good idea, because that will make you panic then. Okay, because for the rest of the questions, then you won't have enough time left. You would end up doing careless errors in them. The diagram shows two particles P and Q which lie on a line of greater slope of a plane ABC. Particles P and Q are each of mass n kilograms. Okay. Let's read the question statement first. P and Q are these two. We have their masses. Angle of inclination is given, sine theta is 0.6, that's 0.75, 3.25, all of that is given. Okay, AB part of this plane is smooth and BC is rough. Coefficient of friction is 0.25. P is released from rest at A, so it starts from rest here, 0 meter per second. At the same instant, Q is released from rest at B. So Q starts from this point. Verify that particle P reaches B 0.5 seconds after it is released with speed 3 meters per second. That's what we need to verify. Okay, how do we do this now? Particle P reaches B 0.5 seconds after it is released. What do we know about particle P? Remember, PQ part of the journey, AB part of the plane, that is smooth. Smooth inclined surface, where weight is the only force acting along the motion. No other force acting apart from the weight of the object, right? In cases like these, you need to remember acceleration is given by 10 sine theta. Okay? You can just write it directly as it is. Acceleration is 10 sine theta. Yes, 10 sine theta. When weight is the only force acting, okay, if there's no other force up in the direction of motion. So there's only component of weight that's making it move downwards, and there's no other force. So acceleration is 10 sine theta. What's theta? Theta is this angle. Are we given the value of sine theta? Yes, that's 0.6. So the acceleration value, therefore, that is going to be 10 into 0.6. Acceleration for this part of the journey is 6. Okay. Now, you're going from A to B. That's the part of the journey that we're considering, right? A is equal to 6. What else do we know? Initial velocity is 0. It started from rest. What else? The time taken is... No, we have to verify that. Okay, so we have initial velocity, we have acceleration, and we have displacement. Displacement is 0.75. Now, we need to verify that the time it takes is 0.5 seconds, and the speed at which it reaches is 3 meters per second. So we have to... Yes, when there's no driving force, and it's not free fall. Free fall is basically vertical motion, but this is also a type of motion under gravity. Okay. A equals 6, U equals 0, S equals 0.75. We need to find final velocity and the time taken. For final velocity, we could use v square equals u square plus 2as. Let's see what that gives us. 0 squared plus 2 into 6 into 0.75. And that will give you the value for v. You can see what that is. What's the value of v? Then you have to find the time taken v equals u plus at. Since they're asking you to verify, another idea is also that you just input all values. Just input all values, including the values that they've given here, and show that the equations are satisfying. The left-hand side and right-hand side, if they turn out to be equal, that will also be sufficient because they're asking you to verify this. Okay, you can also just input the value of v here. You can say v is equal to 3 squared. Just use that here, and then you say, okay, 9 equals 9. So that verifies that velocity is 9. Okay, that's one way to do this as well. But you can find it directly as well. This turns out to be 3. And v equals u plus at, 3 equals u, which is 0, plus a, which is 6, into time. Time turns out to be 0.5. That's the first part. That was an easy part. Now it says find the time it takes from the instant that the two particles are released until they collide. Time taken from the instant that the particles are released until they collide. Now, how do we think about this? You see, P starts its journey from this point, and it starts moving downwards. Q starts its journey from this point, and this is also moving downwards. At some point, they're going to collide because maybe P is moving faster. So let's say this is the point where they collide. Let's call this point something. Let's say this point is X. That's where the collision happens. Okay, I'm calling this point X. Let's say this is where the particles collide. Now, how much time does it take for them to collide? Yes, P initially moves faster, so eventually it catches up with Q because of that, because it has more acceleration in the beginning. Now, what do we do for both the particles? In the first part, we have done some part of this already. We already know what's happening to particle P from A to B, right? We know it takes 0.5 seconds to reach the point Q, right? It takes 0.5 seconds. And at the point Q, its velocity is what? Its velocity is 3 meters per second. That's the velocity of P at this point, 3 meters per second. Velocity of Q, what's that? Velocity of Q. Velocity of Q is 0. It starts from 0 meters per second. Now P has already taken 0.5 seconds to travel to this point. He has already reached this point, okay, in 0.5 seconds. But remember, the two particles were released at the same instant. It said that somewhere here. At the same instant, particle Q was also released. Both the particles were released at the same instant. So when P reaches this point, X, when P reaches this point, Q would have already moved some distance down the plane, right? Because 0.5 seconds have passed. How much distance would Q have moved down the plane? Can we find that somehow? Let's talk about what happens to Q in the first 0.5 seconds. Okay, let's start with that first of all. We're talking about Q. Q is moving down the plane. Okay, I'll connect the charts in another while. Let's hope it keeps working for now. Yeah. Q has traveled 0.5 seconds, so a velocity of 0 started from rest. Do we know anything else for Q? for its motion for 0.5 seconds, we know the initial velocity, we know the time taken, and that's it. We don't have any other information. What we are looking for is how much distance it has traveled already until this point. That's what I want to find out first of all, at how much distance it has traveled already. So I'm looking for S. I need one other piece of information. I need either the final velocity or the acceleration. Can we find the acceleration somehow? We can use Newton's second law of motion to find the acceleration. Yes. So we can use Newton's second law of motion to find acceleration because we were given some information about coefficient of friction. We know the forces acting on Q. What are the forces acting on Q? There is a component for weight. Let's represent those forces here quickly. We've got weight of Q, that is 10 times m. And its component here, since this angle is theta, is going to be 10m sine theta. There's going to be friction that's opposing the motion that acts in this direction. These are the two forces acting along the surface. What else? We've got normal reaction. We consider that in this case because we're talking about friction. We also have to consider that. Then what about the component of weight in this direction? That will be 10m cos theta. Now, these forces are supposed to be equal to each other. R should equal 10m cos theta. These two values are equal to each other. Let's write that down here. For Q now, R is equal to 10m cos theta. Okay, that's one equation that we've got. R is equal to 10m cos theta. We know the value of sine theta already. We can find the value of cos theta from that. If sine theta is 0.6, we don't need exact answers. We can just use our calculator directly as well to find the value of cos theta. So you can do something like this. Sine inverse of 0.6 and then take cos of that. That's 4 over 5 or 0.8. Cos is 0.8. Okay, if sine is 0.6, cos is 0.8. So it becomes 10m into 0.8, which is 8 times m. R equals 8m. Okay, now what happens along the surface? Along the surface, we've got these forces. We've got 10m sine theta and F. Forward force is 10m sine theta, backward force is F, since the particle Q is moving down the plane. So we can say the forward force, we're using Newton's second law of motion now. Forward force is 10m sine theta minus friction. That should equal mass of Q, which is m, into acceleration that we have to find out. Okay, now what does this become? Sine theta was 0.6. So 10m into 0.6 minus friction. Since the particle is moving, when the particle is moving, friction is at its maximum value. It will be mu r. That equals mass into acceleration. 10m into 0.6, that will be 0.6m minus mu. We were given the value for mu here, that was 0.25. 0.25 times reaction, that's 8 times m, that equals m into a. M is appearing in every single term, it will get cancelled out. And we would have 6 minus 2 equal to a equals 4. The value of a turns out to be 4. 0.8 was sine theta. Sine theta was 0.6. We just use our calculator to find cos theta from that. Sine inverse of 0.6, and then we did cos of that, right? So we had sine theta given, find cos from that. Acceleration is 4 now. When acceleration is 4, now we can find the distance that Q has already moved in the first 5 seconds. Because now the acceleration for that part of the journey is going to be 4. Which equation connects these 4 things? S, U, A, and T. S equals ut plus half at squared. Let's input values in that. And it would turn out to be 0 into 0.5. That just becomes 0. Plus 1 over 2 into A times T squared, which is 0.5 squared. That's the displacement. Let's see what this turns out to be. 2 into 0.5 squared, that will be 0.25. 0.25 into 2, that is 0.5. So in the first 0.5 seconds, Q travels a distance of 0.5 meters. That's the distance that Q travels. Okay? What do we do now? So I'm going to remove those forces now. I'm going to remove those forces. And now we focus on this journey. In the first 0.5 seconds, Q has already traveled some distance. It is here now at some point. This distance is 0.5. Okay, so let's say Q is here at this point. So now Q is going to move further, and P is also going to move further from here. P is starting its journey now at 3 meters per second. That was the speed of P when it reached the point Q, when it reached the point B. And Q, from this point onward, from 0.5 second onward, its initial speed, we don't have that. Okay, so we'd also need to find the velocity at this point. So after 0.5 seconds, what's the velocity of Q? We also have to find that because we will need that for the next part of the journey now until they collide with each other. So what's the final velocity for Q after these 0.5 seconds? We can use V equals U plus AT for that. V equals U plus AT. And that will give us the final velocity as well. Let's figure this out. U was 0 plus A, that is 4 into 0.5. And that turns out to be 2. So that tells us that Q starts at 2 meters per second at t equals 0.5. Okay, so now we've got particle P here. It's at the point B right now. And we've got particle Q. It has already traveled some distance, which is 0.5 meters. Okay, I thought I'm doing it very slow already. No. Okay. Any problem until this point? Does everyone get this until this point? Okay. Now until this point, we know P is 5.5 meters behind Q. Okay, P is 0.5 meters behind Q for now. Now, what happens after this point? What happens after this point? We want to find the time until they collide. So at some point, they should be at the same position. Now, what I'll do is, my drawing skills are not very good, but I'll try to show this to you like this if I can, just to make it clearer, because some people might be getting confused by those different lines that I have there. So it's a straight line like this, and the situation is like this, that P is here, and it is moving at 3 meters per second. Q is here, and it is moving at 2 meters per second. Both are moving down the plane. This part, this distance is 0.5. That's what it looks like. Okay, that's what the situation is. Now, at some point, they're going to collide with each other. Let's call this point X. What's the displacement that P has from this point to X? Let's write down what information we've got about P and what information we've got about Q. For P, we know its initial velocity now is 3 meters per second. What else do we know? We know the acceleration. Acceleration for P, that is also going to be 4, right? Both of them are moving on the same plane, and their masses are also the same. So this calculation that we did for acceleration, that's also valid for P when it comes on the same plane. Its acceleration is also 4. What else do we know about P? That's it. Time is common between them. So that's another variable that we can use. If time for P is T, we can say time for Q is also going to be T. What do we know about Q now? For Q, we know the initial velocity is 2, right? We're talking from this point onward. Its initial velocity we're considering as 2. Acceleration is 4. And the time for Q is also T. Okay? Time is common between them. Now, can we find any connection between their displacements? Can you find any connection between their displacements? P reaches the point X and Q also reaches the point X from their current positions. If they have to reach that point X where they collide with each other, P has to travel, let's say, a distance that's SP. Q has to travel, let's say, a distance that's SQ. Which one is bigger? SP is bigger. P has to travel more distance and Q has to travel less distance, right? What's the difference between those two values? 0.5. So we can say SP minus SQ, that should equal 0.5. Or you can say SP equals SQ plus 0.5, right? So distance that's traveled by Q plus this 0.5, that will be the distance traveled by P. And that's an equation that we can make to find the value of T. SP, S, U, A, and T. Which equation connects these four things? UT plus half AT square. Let's use that here. UT, so U is 3 into T plus 1 over 2 into 4 into T squared. That equals, on the other side, we've got SQ, which is UT 2 times T plus half into A, which is 4 into T squared plus 0.5. Now, these two terms get cancelled. What are we left with? 3T equals 2T plus 0.5, and the value of T turns out to be 0.5. That's the value of T that we end up getting. Okay? This is the time taken from this point onward, when they were already at the point B. 0.5 seconds had already passed before this, right? These 0.5 seconds had already passed before this. We wanted to find the time that it takes from the instant that the two particles are released until they collide. What's the total time taken? It will be the sum of those two numbers, 0.5 plus 0.5, and that will be the result. That equals 1. That's the total time taken by those two particles. Is that okay? Does this make sense to everyone? Right? Fairly complicated, but yeah, after doing so many easy questions, it's fair now. Okay, let's move on to the next one, last part. Do particles coalesce? Okay, so two particles merge together, they combine and become one single object when they collide. The coefficient of friction between the combined particle and the plane is still 0.25. Find the time that it takes from the instant the particles collide until the combined particle reaches C. Okay, how do we think about this now? C is this point here. So the collision is happening at the point X, right? This is where the collision is happening, at the point X. Now, first of all, the two particles collide. Now, when they collide, we will have to use conservation of momentum. Yes, we have collision, right? When they collide, we have to use conservation of momentum here. So for that, we need to know the momentum just before collision and the momentum just after collision. Okay, momentum just before collision and momentum just after, the velocity just before collision. Velocity just before collision. How do you find velocities before collision? The velocity of Q and P, we don't have any of those velocities. We'll have to find those velocities. We have to find the velocity of P and the velocity of Q. Okay, how do you find them? Let's find those final velocities for P and Q, for both of them. For P, while it is moving downwards, in this previous case, we knew that U was equal to 3, A was equal to 4, and the time value it turned out to be 0.5. And for Q, U was equal to 2, A was equal to 4 and the time value also turned out to be 0.5. What we can do is we can find the final velocity after these 0.5 seconds have passed. That will be the velocity of the particles at the point of collision, just before collision. That's what we're looking for. Velocity just before collision. U plus AT. That's the equation that I'm going to use here. V equals U plus AT. What does that turn out to be? 3 plus A, which is 4, times T, that's 0.5. And that turns out to be 5. And for Q, V equals 2 plus 4 into 0.5. That turns out to be 4. These are the velocities. Now, this is again just for your notes. Velocities of P and Q just before collision. Just before collision. Now, can we find the velocity of that coalesced particle now, that merged particle? We'll have to use conservation of momentum for that now. Mass of P was m kg. Mass of Q, that was also m kg. Right? Both of them had the same mass, right? Yeah. We can apply conservation of momentum now. Momentum before collision. That should equal momentum after collision. Momentum before collision. What's momentum before collision? Oh, I'm sorry. Thank you so much for reminding. Otherwise, it would have wasted so much time. I hope it doesn't turn off in that time. I hope it survives, because sometimes it ends up going down after charging if it's only 1%. Okay, that's safe now. 2%. Okay, thank you so much for reminding. Okay, velocity, momentum before collision, that's equal to momentum after collision. Momentum before collision, mass of P, that's m, into velocity of P, that's 5, plus mass of Q, that's m, into velocity of Q, that's 4. That equals the total mass, which is 2 times m, into the velocity of that coalesced particle. Let's call that coalesced particle. Yeah, so they're calling that, no, they're not calling that C. Let's call that something. That was PQ. Let's call this coalesced particle S. So that's the coalesced particle, or that's used for displacement. What I'll do is I'll call this PQ. That's the coalesced particle. 9m equals 2m velocity of PQ. So velocity of PQ, that turns out to be 4.5 meters per second. Yes, that's the velocity just after collision. That's the velocity of the combined particle now. Okay. All right. Now that we have it, we want to find the time that it takes from the instant the particles collide until the combined particle now it reaches C. It reaches this point C. Okay, now what do we know about the combined particle? Let's write that information down. For the combined particle, we know that its initial velocity is 4.5. That's one thing we know. Do we know anything else? We know the acceleration. Acceleration on the surface is 4, right? Because the forces are the same. The ratio of the forces is the same. Initial velocity is 4.5. Acceleration is 4. What else? We need one more piece of information to be able to find the value of T now. Do we have anything else? We've got some information about distance, right? The total distance until this point was 3.25. Now, where did this collision happen? Do we know that? We don't know at what point the collision happened. So we would have to find now where exactly the particles collided, right? Because that is where the coalesced particle would start then. Where exactly did the particles collide? What was the point of collision? That's what we have to figure out. Have we found that anywhere before? We have not. So what we would do would be, we would find the displacement for one of these particles as well. Do we have that anywhere? No. Yeah, we don't have that anywhere here for P or Q. Okay, let's find displacement of P in the second part of the journey. So for this, I'm also going to use S equals, using these values, I'm going to use S equals UT plus half AT squared to get the displacement of P. What would that be? U is 3 into 0.5 plus 1 over 2 into A, which is 4 into 0.5 squared. That will give you some value. You can see what that is. Can somebody check this? What's this value? 2. Okay, so this displacement turns out to be 2 meters. Now, what is that telling us? That is telling us from B onward, it traveled 2 meters until the collision happened. So until the point X, the distance was 2 meters until the collision point. This is 2 meters. If this is 2 meters, how much is left after that? 1.25 meters, right? Because the total was 3.25. So since P traveled 2 meters from B onward to X, the combined particle would have to travel 1.25 meters more to reach the point C. So the displacement for that combined particle, that is going to be equal to 1.25. Okay, I'll just write that down like this. 3.25 minus 2, and that's 1.25. And that's coming from here. Okay, now we've got U, A, and S. What we have to find is the time it takes from that collision point until the combined particle reaches C. So what's the time taken? Which equation connects these 4 things? S, U, A, and T. S equals UT plus half AT squared. Let's use that and see what that gives us. S equals UT plus half AT squared. S is 1.25 equals 4.5 into time, which is T plus 1 over 2 into 4 into T squared. And you have to find the value of T. Now, if all of that was not enough, now they want you to solve a quadratic equation as well. So that's 2.5 equal to 9T plus, oh no, this actually gets simplified. You can cancel this out. This gives you 2. So that's 1.25 equals 4.5T plus 2T squared. That's 2T squared minus plus 4.5T minus 1.25 equal to 0. What you would do would be, you would input these values in the quadratic formula. You have to show the step minus 4.5 plus minus square root of 4.5 squared minus 4 into 2 into minus 1.25 whole divided by 2 times 2. And that should give you the values of T. You can see what they turn out to be. There are 2 values that we get. What are the 2 values? One you're saying is 0.25. You should write both of them. Then if the other one is negative, you ignore that. Minus 2.5. Okay, thank you. So time equals minus 2.5. Time cannot be negative. We ignore this. This is what we were looking for. And that's our final answer.